Qatar University Vice President for Research and Graduate Studies, Professor Mariam Al-Maadid. So, Professor Mariam, the mic is yours.
Thank you, Dr. Mohammed Rashidat. Dear ladies and gentlemen, I am pleased to join you in this event, which is the 11th edition of the Material Science and Engineering Symposium. The title of this event, which is Emerging and Enabling Materials, is a very important subject that is highly needed for the society, government, and for the fourth industrial revolution. This is a continuous collaboration between Center of Advanced Materials at Qatar University, Springer's Emergent Materials Journal, Texas A&M University at Qatar, and Qatar Petrochemicals Company, QAP. Very happy to see the academia and industry from all over the world through this common platform where ideas are shared and interacted, which in turn can lead to economic, social, and sustainable development worldwide. Also, glad to mention that Emergent Materials Journal, which is in Web of Science and Scopus, is expected to have a good impact factor soon. Through this electronic platform, I would like to thank all the keynote speakers, moderators, invited speakers, participants, and the organizing team for their time, contribution, and efforts in this conference. Thank you.
Thank you, Dr. Mariam. And now I would like to introduce the Dean of Texas A&M University at Qatar, Professor Caesar Malev. So, Professor Caesar, the mic is yours.
Thank you. Thank you very much. And howdy to everybody, like we say here in Texas. So on behalf of Texas A&M University at Qatar, it is my pleasure to welcome you to the Emerging and Enabling Materials Conference. As you know, this conference is an extension of the annual Materials Science and Energy Symposium that has been a successful partnership with our friends and colleagues at Qatar University for the past 11 years. And we are grateful to the continued support of our partners at QAPCO, the Qatar Petrochemical Company, which generously sponsored the symposium and this conference. Texas A&M at Qatar is proud to partner with academic and industry collaborators such as Qatar University and QAPCO to help realize sustainable solutions to real-world challenges and to encourage the exchange of knowledge, ideas, and expertise that is essential to fuel innovation and new thinking. This conference focuses on material science, a unique field that contributes to many engineering applications that advance our civilization. And this event illustrates the importance of collaborating across industries and across disciplines to develop scientific solutions that have direct impact on the world around us. The speakers and poster presenters will cover a variety of themes and subject areas, including water and the environment, oil and gas, energy conversion, biomaterials, polymers, and composite and construction. And each of these areas aim to support the research grant challenges identified by the state of Qatar. This conference brings together experts from academic institutions, research centers, industry and government, organizations from Qatar, North America, Europe, Australia, New Zealand, and Asia to discuss the latest advances in material science and engineering. Over the course of the past 11 years, the Materials Symposium has been successful in developing a synergy among educators, researchers, and industry in Qatar. I hope that this conference will continue that tradition and serve as a platform to further foster interdisciplinary collaborations and technology breakthrough. Thank you very much, and I hope that all of you have a wonderful multi-year event this year again. Thank you.
Thank you, Dr. Caesar. So as I mentioned, we have 2 sessions every day. Today we have 2 sessions. The first one will be on water and environment. The second one will be on energy conversion and storage. And in between, from 1 to 4, we have poster session. So let's start our first session at 9:30. We will have 7 speakers in the first session and 8 speakers in the evening sessions. So thank you very much, everybody, and I hope you can enjoy our event today. Thank you.
Thank you.
Muhammad Hassan, do we keep the same link, correct, for this session, for your session?
Yes, Dr. Riyad. Shall we start, or so we have all the speakers actually? So what do you think? Shall we start now, or?
Yes, you can start. Introduce your speaker, Dr. Muhammad.
Okay. Okay. Hello, everyone. Thank you, and welcome to Qatar University and Texas A&M joint symposium, annual symposium. We welcome to you all to Qatar. So our first session has very good speakers from both industry and academia as well. We have 4 talks from academia and 3 important talks as well from the industry. So our session is about water and environment, and it covers like a very broad range of topics, mainly membrane technology development and capacitive deionization, as well as applications in the energy and environment that is related to produced water and the processed water treatment. Also, we have a very good talk from the solar water energy nexus. I will start with the first speaker, and it's actually my honor to introduce all the speakers. This session is moderated by myself, Muhammad Hassan from the Center for Advanced Materials, and Dr. Shane, my colleague from the Center for Advanced Material as well. So our first speaker is Professor Song Kwan Hong. He's a professor of from the School of Civil, Environmental, and Architectural Engineering at Korea University. He is also the Dean of Korea University, Korean Institute of Science and Technology, KIST, Graduate School of Energy and Environment. Professor Hong, he received his bachelor and master degrees from University of California, Irvine, and then he joined UCLA for PhD. He got his PhD in 1996. After that, he joined the University of Central Florida as assistant professor, the Department of Civil and Environmental Engineering there, from 97 to 2003. And finally, he ended at Korea University in 2003. His primary research involves the development of membrane technology for drinking water, seawater desalination, water reuse, industrial processes such as ultra water production, and shale oil and gas produced water treatments. He published more than 180 articles in internationally renowned journals with H index of 55, and his articles received more than 13,000 citations. With his expertise in the field, he's also currently the director of Korean optimized reverse osmosis membrane-based desalination integrated with advanced energy saving project. This project has received 25 million US dollars from the Korean government. He also an editor for the Journal of Membrane Sciences, associate editor for journal Desalination and Water Treatment, and also he's in the editorial board of the Desalination Journal. In addition, he has some academic societies activities. Professor Hong is a representative of the IWA Korean National Committee. He is also the vice president of the Korean Society of Environmental Engineers and the Korean Membrane Society. He will be talking to us today about his latest research about the future of desalination, low energy, low carbon, and RO brine valorization. Professor Hong, please go ahead. The floor is yours.
Thank you for great introduction.
You're welcome, Doctor.
Let me share my presentation. Sometimes it takes time, so
Yes,
please be patient with me. I'm not sure why this one is not working.
yeah, we can see it now.
Okay, I'm ready. I hope that you can see this my presentation clearly. Hello everyone, I'm SK Hong. I'm a professor of Korea University and a dean of Graduate School of Energy and Environment. I'm very honored and also pleased to participate and give a keynote speech in online conference on emerging and enabling materials hosted by Qatar University. Although it is unfortunate that I cannot meet you in person due to COVID-19, I hope, hold on. I hope to entertain you next 40 minutes through this virtual conference by talking about future of seawater desalination with an emphasis on low energy consumption of RO membrane-based seawater, SWRO desalination. This is the outline of my presentation. I'm going to start with a brief introduction regarding our future of seawater desalination. And then I'm going to talk about SWRO desalination activity in Korea briefly. Then the main topic of my talk today, low energy desalination. The future of desalination technology can be summarized as low energy and thus low carbon, which is integrated with renewable energy such as solar and wind power. Compared to thermal desalination such as MED and MSF, RO-based desalination produce much less CO2 regardless of the source of energy used. Thus, RO has become choice of desalination technology adopted in the current desalination market. However, SWRO plants still emit tremendous amount of CO2 to the atmosphere, demanding more technical advancement to further improve energy efficiency. This slide shows a typical SWRO desalination process. Raw water is first treated by various pretreatment processes, including DAF, dissolved air flotation, DMF, dual media filter, or UF membrane to remove particles and organics which can cause significant fouling on the membrane surface. The pretreated feed is then supplied to the RO system with pressurization by high pressure pump. Lastly, the hydraulic pressure in the concentrate is recovered by ERD, energy recovery device. The efficiency of HPP and ERD significantly influence the total energy consumption in SWRO desalination. Some of the desalination, SWRO desalination plants in the Arabian Gulf, including the one in Qatar, here are listed in this table. You may notice that the high pressure should be applied due to higher salinity of seawater, and energy-intensive pretreatment process such as DAF is also typically installed and operated. Lastly, second-best RO, such as BWRO, is applied to decrease the salinity further. All of these features increase specific energy consumption, SEC, of the SWRO plant in the Arabian Gulf. In addition to low energy and carbon, out-of-brine polarization is another feature of future seawater desalination. For example, DTRI, Desalination Technology Research Institute of SWCC, Saline Water Conversion Company in Saudi Arabia, has been attempting to develop a series of technology for out-of-brine treatment and utilization. Here in this diagram, NF is first installed to separate monovalent and divalent ions. For some reason I cannot use the point properly here, but that's okay. Then monovalent, such as NaCl-rich NF permeate, is processed by RO and further concentrated by high pressure pump here, and diverse new brine concentrators such as FO hybrid process as shown in this diagram. As a result, magnesium and calcium, other transition metals are recovered from NF reject brine, and NaCl, bromine, and other alkali metals such as lithium can be recovered from RO reject brine. We can produce NaOH from highly concentrated NaCl solution, thus adding value to RO brine. Because of the time limit that I have for my presentation, I would like to focus on energy issue mainly today and hope to have another opportunity to discuss more about various technological advancement concerning RO polarizations. The second topic I'd like to talk about an SWRO desalination activity in Korea, especially my project, the R&D project in Korea. As introduced at the beginning, Korean government launched a huge SWRO desalination R&D project in Korea in 2016. So it's about 4 years ago. Which because I was appointed as a director of this research group and center, and we tried to achieve 3 technological advancements. Number 1, we tried to develop low energy RO system using the world best RO membrane. Number 2, in order to supply very clean water to RO systems, energy conserving algae response pretreatment process is developed. Lastly, low energy future technology for replacing second pass RO is being developed, including CDI, which is the topic of, I guess, Professor Son's presentation in this session. Then we try to develop a 1,000 tons per day pilot plant, and then we convert all of those data to the design of 100,000 cubic meter per day real plant, so that we can achieve the 3.3 kilowatt hour per cubic meter of water produced, which is considered to be very low energy desalination energy consumptions. So we are working really hard for this goal of R&D project, and this research group is known as KORE, as shown in this diagram here. In Korea now, SWRO desalination, first commercial SWRO desalination plant is being constructed in Daesan, which is a large petrochemical industrial complex. And this plant has a size of 100,000 cubic meter per day with a capital investment of $210 million US. And again, the low carbon and low energy, that is one of the objective of this plant. And SEC that we are targeting, that is about 3.4 to 3.6 kilowatt hour per cubic meter of water produced. Fortunately, KORE Research Group constructed a pilot plant as shown in this diagram here, and we performed pilot study in Daesan. Hopefully, some of the data that we obtained can be used for construction and operation of this plant in Korea. We also built pilot plant in UAE, and as I mentioned, this is a size of 1,000 cubic meter per day. And this is actual plant. You know, this is not just pilot plant. And we applied all those 3 technological advancements that we have. And we had a ceremony on October 6, 2021, which is like 1 month ago, for the construction and completion of constructions. This is a schematic of the UAE pilot plant. And the Korea University is responsible for coordinating entire process. And then Daewoo, which is number 3 construction company in Korea, they are in charge of construction of pilot plant. And also K-Water, number 1 water service company in Korea, is responsible for operation of this plant. And Kosong is developing MTBF, which can replace DOF as a pre-treatment. And then Samsung Engineering Company is developing UF membrane process. And then LG Chem, which is known as a company of battery, and they are also making auto membrane, world best auto membrane. And then they provide SWRO and BWRO, which are developed in this project. And then in order to replace BWRO, capacitive deionization technology is developed by C1 Tech in our research group. I'd like to talk about MTF, mesh tube filter that we are developing. This is an energy-saving algal response pretreatment. MTF exhibit similar algal removal performance with DOF. However, MTF requires only 33 to 39% of the energy needed for DOF. So we can have significant energy saving in these pre-treatment processes. Next, I'd like to introduce advanced SWR membrane, which was developed by LG Chem. As you can see from this diagram, LG Chem developed a series of next generation outer membrane, and including the one which has a flow rate of 9,900 with a salt rejection about 99.88. And that is much better than other membrane on the market right now. So we can say that this is one of the world, this is the world best SWR membrane in current market. And actually this one now on the market and being produced in mass quantity. High rate is achieved with the same applied pressure, and the permeate from this outer membrane contains low salt compared to other SWR membrane. This is the simple numbers that we actually applied to design of outer system, which containing this outer membrane. As you can see, after this single stage RO, we can produce the TDS level of 160 to 440 milligram per liter, depending on temperature and the salinity condition. And so we can have significant SCC reduction by adopting this membrane. And then also, as a result, we can have a smaller BWR system, or we can replace this BWR by CDI technology, which is electrochemical desalting technology. And I would say that this is a lower energy future technology for replacing second phase RO, because with the TDS level less than 2000 ppm, normally CDI has better energy consumption, energy efficiency than BWRO. So CDI can remove salt in the range of brackish RO and consume lower energy than BWRO with optimized system or conditions. And so combine all this, technological advancement, and we like to, demonstrate energy efficiency of all of this, the new technology in pilot plant in UAE. Currently, it is in progress. I hope that we can get together at the end of next year. Then I can share the successful story of this pilot plant with you. So now I'm gonna talk about the next item, which is the low energy desalination technology, and that is the main topic of my talk today. Recently, my research group has published a comprehensive review paper concerning energy issue in desalination in the Journal of Applied Energy. In this paper, the energy consumption of full-scale seawater reverse osmosis plant all over the world were critically reviewed. More specifically, more than 70 data sets for large-size seawater reverse osmosis plants were collected, examined, and analyzed. Then major technical trends were investigated and identified. Also, critical factors affecting energy consumption of SWRO were analyzed, and future technical direction was suggested to further reduce energy consumption of SWRO plants. This one is now available in the literature. Now, I'm going to talk about overall technical trend, which were deduced from our comprehensive analysis of real-scale SWRO plant in the world. Increasing capacity and reducing SEC. The trend of increasing capacity and reducing SEC over the last 4 decades, we can observe construction of many large desalination plants after 2000 year, leading to exponential increase in desalination plant capacity. Over the years, not only the capacity, but also the energy efficiency of SWR plants significantly increased with advancement of ERD, as shown in this diagram. The development of ERD significantly reduced energy consumption of SWRO. The turbine type ERD, FT, and PT is not highly efficient. Thus, to further improve energy efficiency, isobaric ERD such as DeVere, or PX pressure exchanger are adopted, as you can see from this diagram. The next, low energy desalination and improved water quality. The next trend identified is the RO configuration for better energy efficiency and water quality. Two-stage RO, treating concentrate of the first stage RO, is designed to increase water quantity. Two-pass RO design, on the other hand, treating permeate of the first stage RO is adopted to increase water quality. As shown in the left diagram in the left, the single stage is more applied in recent years over 2 stages to reduce SEC rather than achieving high recovery. Technical shift from single pass to 2-pass is also achieved to improve higher water quality produced. Now I'm going to talk about critical factors affecting energy consumption from real-scale plant data analysis. Feed salinity and temperature. The effect of feed salinity and temperature, as shown in this diagram, as feed salinity increases, more hydraulic pressure is required to overcome the osmotic pressure of high saline water. Thus, SEC increases with the increased salinity, as shown in the diagram in the left. Furthermore, SEC decreases with the increasing temperature as expected from fundamental theory of outer membrane process. However, no such trend is found in real-scale plant data, since there is a dependence between feed salinity and temperature. For instance, in the Middle East, high salinity is associated with high temperature, resulting in no clear temperature effect on SEC. Plant capacity and pump efficiency. Commonly, if pump size increases, pump efficiency also increases. Our analysis shown in the left diagram presented such a trend. However, it should be noticed that pump size is not always or directly related to plant capacity, since pump is configured to each rack or unit of out-of-line systems. Thus, no clear trend is identified for the capacity less than 100,000 cubic meter per day. I mentioned the ERD played a key role in reduction of energy consumption. As shown, the efficiency of a turbine is much less than that of isobaric ERD. Thus, in the expansion and retrofit of existing desalination plants have been done by adopting isobaric ERD, resulting in significant reduction in SEC. Lastly, permit quality and auto-pass configuration. It is expected that if the number of pass increases, permit water quality is improved. Single pass configuration typically produces 300 to 500 milligram per liter TDS, while 50 to 120 milligram per liter of TDS is produced by two-pass system, as shown in this diagram. However, more energy is required for the operation of two-pass system, resulting in higher SEC. More specifically, SEC increases with order of single pass, split partial second pass, and partial two pass and full two pass in this diagram. Permit quantity, recovery, and also auto stage. This is the last, the slide for critical factors affecting SEC. An increase in feed salinity, as you expected, caused achievable auto recovery to go down. However, if the recovery is enhanced by two-stage configuration, SEC will go up. Therefore, there will be an optimal recovery to minimize SEC. It is between 40 to 50% for single stage, while it is around 60% for the two-stage design. Based on the in-depth analysis of factors affecting SWR energy efficiency, future direction to lower SEC of SWR plants can be suggested, as shown in this diagram. First, since high salinity causes SEC to increase, the dilution of feed salinity, such as osmotic dilution by F4, can reduce SEC further. Second, the energy consumed by pumps can be reduced by improving their efficiency and reducing irreversible work, which is not involved in actual separation process. Third, when we try to increase both quantity and quality of desalinated water, SEC will go up. Since the outer brine becomes more concentrated, in this case, the logical way to reduce energy use is harvesting osmotic energy of a highly concentrated outer brine. So with that, next I'd like to discuss about future perspective based on theoretical SWR energy consumption analysis. Following up our analysis of current energy consumption in SWR desalination plant that I have discussed so far, we performed theoretical analysis and extensive review, and 3 directions were proposed for improving energy efficiency of the SWR process. Number 1, minimize irreversible work of the high pressure pump. Number 2, decrease the osmotic pressure of the feed. And number 3, recover osmotic energy from reverse osmosis RO concentrate. After The feasibility of each approach was identified by assessing the theoretical minimum energy and the maximum available margin. The strategies for each directions were presented with a technical description, then critically evaluated by considering their practical application. This work has been published in the Journal of Membrane Science. Journal of Membrane Science. I think this is available in the literature right now. The first, I'd like to talk about the first option to reduce SCC, that is reducing thermodynamic reversibility associated with auto process. The method to reduce irreversibility of high pressure pump used for auto process can be categorized into number 1, multi-staging, number 2, semi-batch, and batch configurations, as shown in this diagram. The energy supplied to our system is used to separate from seawater feed, and an additional different type of work is also associated with process that is not directly involved in separation. This work is equivalent to the energy lost by entropy generation, which is known as irreversible work. To minimize the irreversible work, energy should be supplied in a staged manner rather than all at once. For this purpose, stage design have been developed to increase hydraulic pressure gradually. However, the current SWRO desalination plant with multi-stage RO do not show such low energy consumption. This is because the multi-stage configuration is employed mainly for high recovery. To overcome the installation difficulty of infinite multi-stage RO, semi-batch RO, named closed circuit desalination (CCD), was proposed. The CCD configuration adopts cyclical process where the concentrate is continuously recycled as a feed and mixed with fresh feed until the desired recovery can be obtained. Lastly, batch system can minimize irreversible work by gradually increasing the hydraulic pressure as well as reduce the generation of entropy by mixing. Therefore, batch RO would be the most energy efficient process from theoretical point of view. However, the implementation of an ideal batch operation is limited, thus face operational challenge in real-scale systems. This slide shows SCC comparison of multi-stage and batch RO design. In this figure, y-axis represent change in flow exergy of RO design, and x-axis describes the recovery of seawater desalination process. Under ideal condition, batch RO equipped with a variable feed volume consumes the lowest energy close to theoretical minimum energy required for desalination due to minimized irreversibility of batch operation. However, semi-batch RO consumes more energy due to entropy generation, which occurs. The fresh feed is mixed with the concentrate. Overall, a staged RO design consumes less energy than conventional single-stage RO. From the point of practical operation, two-stage RO would be practical solution for minimizing the irreversibility of high-pressure pump. Now, the next improvement strategy, that is decreasing osmotic pressure. If it were possible to reduce the osmotic pressure of the feed, the corresponding hydraulic pressure required to produce a certain amount of water would be reduced, resulting in lower energy consumption. These approaches can be categorized into direct and indirect method, that is, dilution of the feed stream, which is direct, and reducing the relative osmotic pressure difference, which is indirect method. The dilution of feed stream can be also done in two ways. The first is to make recycle stream by using low concentrate water, such as permeate from first pass or concentrate from second pass in the SWRO process. The second way is to utilize additional feed stream, such as treated wastewater or brackish water, as shown in this diagram. This is something that we developed in our research group. Single partial, single pass SSP RO to produce pure permeate while maintaining the low energy of single pass RO. We proposed a new RO configuration, so-called split partial second pass SSP. In a PB, the front RO module produced pure permeate while the rear permeate is more saline. SSP is then designed so the rear permeate is recycled to the feed to dilute. In this way, only front permeate is collected, which is relatively low in salinity, and the rear permeate is mixed with the feed to reduce osmotic pressure of the feed stream. The dilution not only lowers the feed osmotic pressure, but also allows the system to produce low saline permeate from the diluted feed. Thus, purer permeate is obtained without using second pass RO. It is noticeable that SSP consumes less energy than two-pass RO configuration. Because there is no second pass to operate in SSP, energy and expense can be saved. As a matter of fact, this technology is patented by our group, and then it is now transferred to industry. So I think that we can see this one in the market pretty soon. The next slide shows FORO hybrid process in which seawater desalination is integrated with wastewater reclamation facility through FO process for low energy desalination. The first benefit of the FORO hybrid process is a reduction in the thermodynamic energy requirement by simple dilution of seawater with a treated wastewater effluent. In addition, the RO and FORO hybrid system provides the opportunity for wastewater reuse with less energy use. In this hybrid process, wastewater is treated by FO process using the osmotic pressure of seawater, reducing energy consumption for wastewater reuse. However, despite the benefit in terms of energy savings, several problems may occur in realizing this technology. The public perception of the use of treated wastewater in the mainstream water supply is a major concern. In addition, the FORO hybrid process requires desalination plant and wastewater treatment plant to coexist at the same site. Furthermore, large amount of wastewater is required to derive the FO process as shown in this diagram. For instance, to reach 50% dilution, theoretical energy decrease of approximately 0.63 kilowatt hour per cubic meter per day, a cubic meter of water produced, the amount of wastewater feed should be approximately twice that of the seawater feed stream. So it requires a large amount of wastewater. Lastly, the additional capital and operating cost for the FO process should be considered. Recently, new process to utilize draw solution with lower concentration than the feed stream has been developed to reduce applied pressure. This process can reduce the relative osmotic pressure difference between seawater feed stream and draw solution stream by situating these solutions, seawater and low concentrated draw solution, on the either side of semi permeable membrane. This process is called draw solution assisted reverse osmosis, DSARO process. In first RO stage, seawater is dissolved and fresh water is permeated into draw solution side. So seawater desalination is achieved at this moment. In the second RO stage, pure water is produced from the diluted draw solution. This new process has been identified as an energy efficient, high recovery process for the treatment of water with a high salinity, although this configuration is still under development and no suitable membrane for DSARO has been developed. Lastly, reducing or recovering osmotic energy. The fourth step
Professor Hong, are you with
as
us?
shown in this diagram, address the matter of
Okay.
disposal and extract energy by using the concentrate. PRO, pressure retarded osmosis, generate energy by utilizing the salinity gradient. As a result of the process, the original high saline solution is diluted and its osmotic energy is converted to hydraulic energy, which can generate electricity when used in hydroturbine. Osmotic energy can be also harvested by RED, reverse electrodialysis, which adopts selective ion exchanger membrane to control ion permeation. RED exhibits a higher power density than PRO for seawater and river water, whereas the power generation of RED is less for the high saline water and river water pair. However, the amount of energy produced with seawater and river water pair is still low for practical application. The application of PRO in practice is still challenging because PRO utilized low saline water. SWR plant should be located where a sufficient amount of low saline water can be supplied, as shown in this diagram. The feasibility of osmotic energy recovery is not high enough to realize commercialization at present. However, potential for the osmotic energy recovery process is still good considering the extent of possible reduction in practical operations. If factors affecting this maximum extractable energy reduction can be improved, the amount of net energy generation will increase beyond the point of economic feasibility. This is a concluding remark. The maximum available margin and actual achievable energy reduction on the SCC of SWRO in each improving technical option that we have discussed in the presentation as shown in this slide. Based on this analysis, primary conclusions are summarized as follows. Minimizing irreversibility is effective, but operating issues are challenging. Decreasing osmotic pressure can be effective only with additional low saline water. Recovering osmotic energy may be effective, but needs to be further developed technologically. We are still running it really hard to further reduce energy use in SWRO desalination to reach theoretical minimum energy consumption for seawater desalination. So we're still working really hard every day. Thank you for your attention and participation in my presentation. Be healthy and strong against the COVID-19. Also, see you all in person in the World Cup 2022 in Qatar. Thank you very much.
Thank you, Professor Hong. Thank you so much. We look forward to see you next year, actually, around this time, one year from yesterday. We look
Exactly.
forward.
That's why I have the final slide like this.
Yeah, yeah,
I
we look
love
forward to.
cycling.
Oh,
love
great!
football.
Yeah, yeah, and it seems that Korea will be able to make it. So hopefully we can see you next year, inshallah. Yeah. So
Great.
yeah, yeah. Thank you, thank you. This is very informative, very good talk. Audience, please, if you have any question, please raise your hand or just write it in the chat. We have plenty of time here, actually. We have about 10 minutes for questions to Professor Hong.
Can I ask a question?
Yes, go ahead.
Yeah, Professor Hong, yeah, it's a really nice talk and good to see you.
Good
So
to see
I
you.
have a very simple question. So during your presentation, I mean, it covered wide spectrum of this desalination, covering this the different configuration and also the material. So one of your slides, I think the second part of your talk, you mentioned about the very efficient the LG Tech membrane, and which have a very high the flux, right? So I mean, is it still traditional, the TFC membrane, or something like is a different different material? Do you know the material of this?
Yes, you know, LG Chem actually purchased Nano H2O company, and the first generation is more like a, I would say, Nano H2O membrane. But the second generation, Gen 2, as you see from this table, they add, new coating technology. So basis is a polyamide membrane, but however, they have some new coating technique applied to synthesize this membrane. So now, high rejection with a high permeability.
So
I cannot
I
say,
cannot, it's a kind of a
the
nano-composite membrane?
I mean, I cannot say exact, the chemistry of this membrane.
Okay,
And
yeah.
then, however, yes, this basis is a polyamide, but however, different coating and then different structure.
I see.
That's all I
Okay,
can
yeah.
say at this moment. Okay.
Right, right. And also, I mean, in the later part of your talk, also you mentioned the new the configuration called the DSARO, and
Okay.
yeah, it's interesting. But also, I think you also mentioned that still, of course, when we develop a new this the system, we need a membrane which can work with this our hypothesis and also our idea. So what do you think? What kind of membrane can be the idea for your DSARO system?
FO membrane, we need to reduce S factors. When you're doing that, you have some problem with the integrity. And DSARO process requires for the osmosis membrane with higher integrity. So it is very difficult to make such membrane. The S factor should be very small so that you're going to have better performance in terms in the water production. But at the same time, because you are applying pressure, this FO membrane or PRO membrane, whatever you're going to say, this the membrane should have certain integrity. So that's why I said the membrane which can be suitable or ideal for DSARO has not been really developed, in my opinion. Also, very difficult to develop.
All right, so look forward to learn more your new system developed in the future then.
Correct.
All right, yeah, thank you.
Thank you. Thank you for your questions.
Yeah, any more questions from the audience?
Dr. Joy, he asked in the chat a question.
Oh, okay.
Yeah,
so yeah, I can read it, Professor Hong. So do you think, this is from Joel, he's from ConocoPhillips, Qatar. He will give a talk later. Do you think that he's asking, do you think BRO could reach commercial stage in the next 10 years?
Oh, that's a good questions. Oh, I hope so. Yes, I hope so. I mean, PRO membrane is, in my opinion, is easier to make compared to F4. But at the same time, I mentioned in my presentation, it requires a large amount of, the additional water stream. That is very difficult to achieve. I mean, difficult to get. And that's why, I mean, technologically, yes, I think the PRO process can be commercialized, but I don't know whether or not this will become mainstream of seawater desalination, because it requires large amount of additional low salinity stream normally can be obtained from wastewater treatment plant. So co-location of wastewater treatment plant and seawater desalination plants, that is required for commercialization of this technology.
Thank you.
So
Thank you. Good feedback. Thank you, Doctor.
Your question.
Yeah, thank you, Joel. So there is another question, Professor Hong, from Jassim Ibrahim. So can the specific ionic composition of the water affect the SEC or the nature of the membrane or configuration?
Oh, I see. Specific. I mean, theoretically, the salinity, I mean, the osmotic power, osmotic energy of the solution will have significant impact on SEC. So yes, I mean, if you have more divalent ions, then that causes more, osmotic energy or most osmotic gradient across the membrane. So that's why I would say yes, solution composition is also affecting SEC. And the practical standpoint of view, if you have large amount of divalent ions, like divalent cations or anions, then it's going to affect operation of RO process due to scaling potential. So that's gonna cause some problem with the fouling issue, which means, eventually it's gonna have some kind of some impact on SEC energy consumption. So I can say in two ways: operational and theoretical.
Yes, thank you. Any more questions from the audience, please? Dr. Shane, please go ahead.
Yes, thank you very much, Professor Ho. Your presentation is very impressive.
Thank you very much.
Instructive the audience, I believe. Yeah, nice meeting you. Yeah. So actually, Qatar has two big SWR plants in Halu area and Abu Pontas. They has a lot of the water production capacity. So anyway, the Qatar select to apply SWR process, sometimes hybridized with MSF to utilize the all power plant facility. Anyway, our Karama is Qatar water energy sector set to the boron removal efficiency of 0.5 ppm. I believe it's very very hard regulation to control the boron in seawater, even in the out of product water compared to other GCC country. I believe that set to 1 ppm like UAE. So my question is, you already demonstrate, install and demonstrate the good facility of a pilot plant. You say that pilot plant, actual plant. So and yeah, in the second pass RO, yeah, we applied the second pass RO to maximize the removal of boron. But your the process replace the second pass RO with the MCDI. So we are very interested how much your plant can remove the boron up to a certain level. So would you
Okay.
give us a good comment?
I can say two things. Number one, the LG Chem membrane, I mean the outer membrane that we developed in our project by LG Chem, it is also high boron rejection membrane, 95%. So I would say if feed boron concentration is 5 ppm, then 0.5 barely we can meet that the requirement just by having the outer membrane maybe single stage. But the if we cannot meet that 0.5 the ppm requirements, then yes, we can use CDI or even BWRO. And however, CDI, I think Dr. Professor Son will talk about this, bromide or this issue, rejection issue, more properly. But yes, by having CDI, we also can reduce further the boron concentration. So I say, with a newly developed outer membrane, as long as the feed concentration, boron concentration is less than 5 ppm, we should be able to meet that requirement. If boron concentration in feed water is higher than 5 ppm, then yes, we need to have additional treatment process like a BWRO or CDI. But from what I see from CDI performance, I think the CDI can reduce the boron further and below the concentration limit, like 0.5 ppm.
Thank you very much. So I have one more question. So in the last section, you mentioned the energy consumption of RO, PRO case, and also I'm interested in RED because, as you know, all the GCC country industry produce a lot of the different types of water. Even they use the RO process to treat their own processed water. So anyway, the all kind of industry, release different salinity level water streams. So also I believe the RED sometimes is more practical or is good for energy, generation in Qatar case rather than PRO. This is my opinion. So how do you think in the future what process RED or PRO will reach the good level in commercialization step?
Okay, if you know this answer, just let me know. We're still in the process of evaluating which one is better, depending on salinity and depending on the amount of water used for this process. So I just avoid my answer for that because there are so many uncertainty at this moment. I would say PRO, but there are many studies that have different opinion about that one. So.
Okay. Yeah.
Okay.
I have
Yeah.
last question. It's okay, Dr. Mohammed Hassan?
Yes, we still have time.
Yeah. I'm interested in the
I have plenty of time, so I love to have questions. So
I like the your project. So your treatment process targeting, I believe, some algae. Gulf also experienced one time, early 2000, the algae bloom. So also we have the water security when we experience the oil spilling. So how? I want to hear your opinion. So your the plant can depending well the oil spill disaster like this situation.
to be honest with you, we haven't really tested any possibility of oil spill in seawater with our developed technology. So I cannot say whether or not MTF mesh tube filter can actually respond to this oil spill crisis well or not. And that's the reason why the DOF is installed in typical SWR plants, even though we haven't really experienced algal bloom lately. So I don't know. I mean, mesh tube filter, we haven't tested, the oil issue yet. So I cannot answer for something that I don't know with the mesh tube.
Okay, thank you very much, Professor Hong.
Thank you, Dr. Shane. Professor Sean, go ahead, please.
Yes, thank you, Professor Hong, for the wonderful presentation. Yes, this is always
There are
very
many questions
inspiring.
concerning CDI.
Yes, you're right. Shidia, I will cover the Q&A session. So my question is about, we have a very important breakthrough of desalination. So first one is the RO membrane using polyamide, the thin-film composite. Second breakthrough is the ELD, energy recovery device. And then now it's time to make another breakthrough, third generation of desalination. So people look at the RO brine, which is the more about resource recovery, like lithium or some of the valuable materials. So yeah, you cover a lot of low energy, low carbon desalination. So in the third breakthrough of the desalination, in your opinion, many people believe this brine, the resource recovery, will be the next target for our seawater desalination to make a more value out of it. So, what's your opinion? What's our next most important research and then possible commercialization? Yeah, except your wonderful presentation. What's the target we have to see more future of the desalination?
I mean, the title of my presentation is low energy, low carbon, and out of brine polarizations. So I concur with your comments. Third, the wave of new seawater desalination is concerning the out of brine polarizations. I don't know whether or not this can be commercialized quickly enough to make significant impact on our SWR practice in next 10 years. I mean, this diagram is taken from my experience with SWCC, DTRI, as I mentioned in my presentations. They are developing, technology that can add value to our brine. For example, we can produce NaOH if we can concentrate our brine, I mean the NaCl solution, all the way up to maybe 220,000 or 250,000 ppm. And that is not really easy to do. I mean, you have to have a high purity, which means you have to take out all divalent ions from NaCl solution, and then you need to concentrate this one all the way up to 220 or 250,000 ppm by using various techniques. I mean, right now, ultra high pressure RO membrane has been developed, but as far as I know, I guess 120 bar or even 150 bar is the maximum pressure that we can apply to this, ultra high pressure RO membrane process. We still need to have like 200 bar, hydraulic pressure to overcome the osmotic pressure of this highly concentrated NaCl solutions. So today's, we talking about, I mean, this conference is for materials. So we need to have certain material which can withstand this ultra high pressure, like a 200 bar, more than 200 bar. And if we don't have some breakthrough regarding, ultra high pressure membrane or the F4 membrane, we may not be able to achieve this, the out of line polarization in commercial sectors. And that is my opinion. And also, here's another thing, NF membrane. If you try to use NF membrane as a pretreatment in this process, then what we need to have is complete removal of divalent ions and complete passage of monovalent ions. I don't see such NF membranes available in the market right now. So we need to have the membranes, NF or RO membrane, which can achieve the role of each process in this out-of-line polarization process. So that's why we are here to talk about materials. Do I answer your question?
Yes, absolutely. You answer, because the answer is nothing. You cannot answer this one. If you answer this one, you would have been very great your effort for the desalination. Yeah, but it's very much reasonable to have a high pressure RO 200 bar. That could be next target. Also, we can see the more opportunity, because now desalination is very established. So we need to look at another breakthrough to have a more energy efficient, also effective way of the desalting process, so that that's our generation. We can try to drive another impact of the desalination plant in the next couple of decades, right?
That's right.
Yeah.
Yeah.
Okay.
I agree with you. Thanks, Professor.
Yeah.
Thank you for your questions.
Yes. Any more questions? So if no more questions, I got one actually, Professor Hong. We are really happy to have you with us. You are one of the world pioneers in the field of desalination. It's a very good chance, very good opportunity. So for the DSA RO membranes, you mentioned about the integrity. This is like mechanical integrity, chemical integrity. What kind of integrity you are,
I would say
talking about?
mechanical integrity is the first thing that we need to look at. And also chemical integrity, yes, I mean, depending on application, chemical integrity is also important. But I mentioned, about, pressure applied to this process. So you have to have integrity as well as, the transport, see, I mentioned about S factors. So in order to have higher permeations, you have to reduce S factor. But by doing so, you're going to lose mechanical integrity, stability. And so that's what I mentioned, the integrity issues.
Yeah, perfect. Also, another thing on the LG Chem, the new membrane that developed the polyamide one. So what is the lifetime of this one, Professor? Especially under the especially as the high temperature of
yeah, this one is just on the market, and then I'm not a representative of LG Chem, so I cannot mention this one.
Okay.
And as far as I know, they tested this one in the Middle East for several pilot plants. And as far as I know, they are doing pretty good. But like what I said, this one is just on the market, and then we are also testing in progress. So I can tell you the lifetime or lifespan of this membrane maybe next year.
Yeah, we look forward to that actually. We look forward to that, and we look forward to see you as well in person next year in the World Cup. Thank you, Professor. We're really honored to have you with us. Yeah, yeah, we're really honored. Yeah, thank you, Professor. Thank you so much. So now we will move on. We are on time actually. So our next speaker is Joel Munir Matar from ConocoPhillips, Qatar. So Joel will present on behalf of Dr. Samir Adham. Joel is a senior engineer at the ConocoPhillips Global Water Sustainability Center in Doha. He has a master's degree in environmental engineering, 2008 from University of Illinois, Urbana-Champaign in the US. Also, his expertise in the area of industrial municipal wastewater treatment and with focus on technology of emerging technologies for water reuse. Currently is responsible for leading and conducting research and process development for both treatment of produced water from oil and gas operations and for the desalination of seawater plants. Joel, please go ahead. We are glad to have you with us as well.
Thank you, Dr. Mohammed. Thank you for the introduction. Can you hear me well?
Yes, sure.
Okay, perfect. So, as Dr. Mohammed mentioned today, I'll be talking about advanced water technologies for the oil and gas industry. I'm presenting on behalf of Dr. Summer. He tried to be here today, but he had other commitments, so he couldn't make it. So, anyway, water is a very important commodity, a very important asset, and is used a lot in the oil and gas industry. I mean, in this industry, for every barrel of oil that we take out of the ground, we get 3 to 4 barrels of water. And that water has to be treated and somehow disposed or reused. There are some beneficial reuse of produced water, and that includes enhanced oil recovery, what is called also water flooding. And this when we put the water back into the reservoir where it came to basically push the oil out and be able to get more oil when the field is kind of depleted. I think the extra water helps solubilize the oil and you get extra oil coming out. It also used to maintain the reservoir pressure. I mean, when the oil come out, pressure sometimes decrease. If you put the water back, you keep the pressure stable. And in unconventional resources in the lower 48, it's used for drilling, especially drilling horizontal wells, and also completion of the well. Now, those are very good applications of produced water, but since we have so much, we are trying to find future innovative options to use this water for. Now, produced water have different characteristics and is valuable. For example, there is produced water that comes associated with the oil production from oil fields, and also produced water that comes from gas field operation. In oil field, the produced water is characterized by having high total dissolved solids. It could reach up to 250,000 milligrams per liter. While gas field, since it's condensed water, the TDS is usually below 5,000 milligrams per liter, making an easy target. Now, both of them are available, and if we can reuse both, we usually try to find application for both of them. Another difference between the two is the total organic carbon. The oil field could reach up to 2,000 milligrams per liter, and that sometimes could be challenging to remove, especially with membrane process. In gas fields, it ranges up to 500, from 12 to 500 milligrams per liter, which is also most feasible to treat. Now, currently, the oil and gas industry is treating produced water to a certain extent, and is limited mainly to suspended solids and dispersed oil and grease removal. And those includes basically API separators that separate the oil and the water just based on gravity. Very simple technique, doesn't remove dissolved oil, but it removes the bulk oil. They also use coalescers that basically make the small tiny droplets bigger and remove it by gravity. And one of the most common ones is hydrocycle, that basically take advantage of the centrifugal force to separate the oil and the water. Now, for advanced reuse of produced water, we need to have a toolbox with advanced treatment technologies to be able to tackle other challenges besides the bulk oil separation. And that includes dealing with emulsified oils. I mean, the water have the oil, sometimes there are some chemicals or surfactants that make the oil emulsify and make it very difficult to separate by normal technologies. Also, the toolbox have technologies to handle high salinity streams, because some of the produced water could have up to 250,000 milligrams per liter. The sulfur organic is another issue. I mean, you cannot dispose or putting any system organics in the water. It could be so dangerous for health. Trace metals is another challenge, as well as production chemicals. The produced water usually have either corrosion inhibitors or emulsifiers that could potentially present problems to treatment process like resins or membranes. Now, one of the key items on the treatment toolbox are membranes. Membranes are technologies that can be treated by different levels, like we have microfiltration and ultrafiltration that are used to remove suspended solids and also certain amount of oil droplets. There is nanofiltration that can remove divalent ions, reverse osmosis that can basically do complete salination. And there are other technologies as well, membrane distillation to get basically clean water based on temperature gradient, pressure osmosis and forward osmosis that you heard in the previous presentation as well. So those technologies can be applied into the oil and gas industry to be able to get further treatment to the produced water for different reuse applications. In this presentation, I will present one case study on the application of ultrafiltration membrane to remove emulsified oil from produced water. And this project is a QNRF project, have been done in collaboration with CAM, the Center of Material Catedral University, and also University of Houston in Texas, and also the Water Sustainability Center. And I will present some of the approach we did to be able to try to adapt these technologies that use novel membranes to see how it can be applied within the oil and gas industry. One of the key aspects of our testing is we have to determine an appropriate protocol that can be used to test these new novel products. The protocol was basically developed first by evaluating commercial membranes that are currently in the market and tailored to remove this emulsified oil. And we focus on different chemistry in different pore size and different membrane characteristics. With those, we developed a protocol to test those membranes, and one of the challenges was developing an appropriate synthetic solution. I mean, ideally, all the tests should have been done with actual produced water. But getting access to high volume of produced water sometimes could be challenging, even for us in the oil and gas industry, because transportation and logistics. So we try to find a solution that can actually mimic as close as possible the performance of the real water. Then we develop a system where we can test the novel membranes, and we focus on measuring the amount of water coming to the membrane, as well as the rejection of contaminants, like organics, as well as the other contaminants that could be present in the water. And another factor was the cleanability of the membrane. I mean, all membranes could get foul, but we need to have a procedure to be able to remove the foulant, because if not, then the membrane cannot be reused again. So we focus on two different cleaning methods here using sodium hydroxide and sodium non-desulfide surfactant. Surfactants are known to be able to remove oil, trap oil to the membrane. And we applied then the protocol once it was validated into the commercial membrane. We apply those to novel membranes like block copolymer or graphene to see how they perform compared to the state of the art. Our hope is usually to get a better product that can have either higher flux or more rejection and very good cleanability. Now, as I mentioned, one of the challenges we faced was finding an appropriate solution to be able to use the testing. The solution needs to have brine, which has to be similar to the brine in the target water we want. Also oil. There are different oil sources in the literature. I guess some of you have seen in papers that people prepare different synthetic solutions. Some people use canola oil, some people use motor oils. We have to find one oil that is representative of what is actually present in the actual produced water. And also we added a surfactant. It's basically a chemical that creates emulsion that make the oil to be more difficult to be removed. And solutions have to be also tailored to different type of membrane. It could be either hollow fiber, flat sheet, and spiral wound. So now I mentioned this sort of oil could be tricky. We tested and compared different oil sources and to see which one of them is closer to the actual produced water. And this is all actually was published in our article in SCS Omega this year. So in this test, we evaluated 3 different solutions. One was actual produced water from one of our operations, a synthetic produced water using crude oil as the source of organics, and also we evaluated another synthetic produced water using motor oil. It's a common oil you can buy from the market. It's used in a couple of tests. We decided to have a comparison between them. So in our experimental protocol, we basically tested the membrane Amicon cell, and we measured the water productivity, what is called water flux, and the units are LMH, which means liters of water going through the membrane per meter square of membrane per hour, and we normalize that by the applied pressure. That way we compare all of them at the same conditions. We first conducted a test on the clean membrane, just using the ionized water to see what is the baseline productivity of the membrane. This membrane is a polyethyl softener membrane, 0.2 micron. And we managed to get 11,500 LMH for the clean water. When we put our actual produced water, the one goes from the field, the flux declined to around 3,000. And then to assess if the membrane flow can be removed by just clean water, we did another clean water test. In this one here, it's called the foul membrane clean water test. We only got 263. Membrane was definitely foul. We tried doing cleaning using SDS and NaOH, but the flux only reached 2,500, so the cleaning was not effective. We did the same test with the crude oil, and we got very similar results. The clean water flux was around 11,000. When we put the synthetic produced water, we got around 3,000, quite close. When we did the foul, the clean water test was 280. And then when we do chemical cleaning, it was the same. The chemical cleaning could not clean the oil in the membrane. However, when we tried the synthetic solution made based on motor oil, the clean water flow was the same, simply the same membrane, but the foul membrane was not that much. The motor oil did not foul the membrane as much, and because some of the organic in the motor oil are some additive that it could either go to the membrane or don't adhere to the membrane as much as the oil. And then when we did the clean water after the motor oil test, the flow was around 8,000, not much decline. And the cleanability was not bad. I mean, so you might have to get better performance, but it's not representative of what you will get in the actual produced water. For that reason, we emphasize that the best way to test the technology is actually using a solution that is close to what you will find in the field. We also took this protocol and evaluated the commercial UF membrane, polyethyl softener as well. These have a 500 kilodalton molecular weight cutoff. And we evaluated one versus a novel UF membrane developed by the team. It's a block copolymer membrane. And for the commercial membrane, we got an initial flux in clean water flow with the water of 3,800. And then we run 3 cycles in this case. We run it one time, then another and another to see the long-term performance of the membrane, I mean, to see if it cumulative fouling. When we run the produced water with the crude oil, we saw a decline of the flux to 2,500. When we did the clean water flux after the produced water, we got 2,800. But the interesting part is it was all cleanable when you use SDS and NaOH. So the membrane, commercial membrane, can recover its own flux, which is a good sign. And we went to the same cycle, the second cycle, and we saw a decline in this time in the flux. Slightly slower in the second cycle, but all of it was cleanable as well. It's a good sign. I mean, if the membrane flux decline, as soon as you clean it, you go back to the original number. The third cycle, again, you see even more fouling. It went this time to 1,400. The clean water flux after the synthetic produced water was 2,300, but it was all cleanable. Now, this membrane has a rejection of total organic carbon, which is basically the parameter we use to monitor the oil and the SDS in the water, of 87%. Now, when we tested the novel membrane, we got a 30% higher flux. It managed to reach 5,500 just with the clean water flux. And you can see the same when you use synthetic produced water and the clean water after. So the flux is higher. But the decline with the novel membrane is less than what happened with the commercial membrane in having some inherent advantages. As well, when we go to different cycles, different runs, this novel membrane have less decline. It's basically all around the 5,000 range, and it's also very cleanable. So it was a big improvement compared to the state of the art. Not only has higher flux, but also you see less decline over time. The only difference was slightly less rejection on TOC. I mean, and that is mainly to the surfactant. I mean, both of membranes rejected the oil quite well, but they have little less rejection with the surfactant compared to the commercial one. But the advantage of the flux is definitely a significant one. So, as a final remark, I want to say that cost-effective water management is key part of the oil and gas industry, since we handle more water than oil. Regulation and water scarcity will drive more treatment and reuse of produced water. A toolbox of advanced technology, including membrane processes, need to be developed for suitable applications. And emerging membrane processes with engineered nanomaterials can provide a step change in performance, which will also be tested on the cellular field conditions. And capacity building and innovation in Qatar are key outcomes of our applied research program. And this project was a good example of capacity building and innovation and teamwork as well. You can see this is some photos of the team. And we would like to acknowledge our API of the project, Dr. Mohammed from CAM, Dr. Karim from the University of Houston, Dr. Samer from the Water Center here, and Dr. Miriam Almadid from CAM as well, that's not present on the photo. We also would like to acknowledge the team at QU, Jara and Ali for the contribution on the project, also Deepak, as well as the team for the Water Center, Altaf, Darin, Mashal, Naveen, and Ari. So, and thank you very much for participating in this conference. And if you have any questions, please let me know. Thank you very much.
Yeah, thank you, Joel. Very nice contribution, and we'll be glad to always continue working with you in those aspects.
Thank you, it was a good project. So.
Yeah, sure. And, so, any question from the audience, please?
I guess all was clear.
Okay, okay. So I would have one actually, like
yes, of course.
For the protocols that we developed that you developed actually at Konoko. So can it handle the suspended solids like the TDS, total TDS? Have you considered that too?
Yes, we handle TDS. We didn't add suspended solid, but if needed, can be added by adding silica powder. The reason why it didn't add TSA suspended solid to a solution is because we assumed that would be removed by the pre-treatment. Before going to the UF membrane, you typically have a cartridge filter that removes particle of 1 micron or 5 microns. For that reason, we do not add it, but if needed, you can add some silica particles, different sizes, to simulate the suspended solids.
Yeah, perfect. Perfect. Thank you. Thank you so much.
No problem.
Thank you. Thank you for being with us today, and we always look forward to continue our
thank you for the invitation, guys.
productive collaboration. Yes, I think we are ahead of the schedule. We'll just hopefully we can just finish a little bit earlier. So we'll move on to our next speaker, Professor Ho-Kyung Sean. Sorry if I'm misspelling some of the names. Professor Sean, he's the director of the ARC Research Hub for Nutrients in a Circular Economy, NICE, in ICE, and the Deputy Director and founding member for the Center for Technology in Water and Wastewater at the University of Technology, Sydney, UTS. His research interests include membrane technology, water treatment process for water reuse and desalination, resource recovery and environmental nanomaterial, physico-chemical processes and environmental applications. Since 2000, Professor Sean is externally engaged as the president of the Membrane Society of Australia, and also he is the editor, one of the editors for the journal Desalination. He co-authored one book, 31 book chapters, and over 420 journal articles, 3 patents. His articles received a citation of over 17,000 citation, and his H index is 69. So he's another world pioneer in the field of water treatment. And welcome, Professor Sean. We are glad to have you again. Actually, maybe within a few months, we have you earlier, like 3 months ago or so. So we are glad to have you again with us here at the Qatar University and Texas A&M. Welcome, Professor Sean. Okay, please go ahead.
Thank you, Mohammed. Thank you, Shane, and the organizing committee to invite me for this very interesting conference and emerging and enabling materials. So today my talk is about membrane, MCDI for desalination. I want to have a little bit of progress for this technology. These are contents, background, a little bit of what's the CDI, and then how we have progressed. And already Professor Hong applied some of the useful technology after first pass, and then we can replace the second pass for this is MCDI. And then I also tried to give a different aspects of the bromide removal using MCDI, and then sharing what's the future of MCDI. Already, CDI is not really fully established. There is not really big scale and full scale, more than 10,000 cubic meter per day. Mostly they are less than 100 cubic meter per day, very small size. So what's the future of the MCDI technology? And then research gap, and we'll complete this presentation. So CDI consists of the graphite and carbon electrodes and spacer, and as same the configuration, and then they are connected with the direct current. And this is the emerging technology suitable for low saline water, less than 5 grams per liter. Also relatively very quick process, and then efficient removal of charged ion, but non-charged ion cannot be removed from CDI. And this is the ideal technology for decentralized and small-scale system when you're attached with the renewable energy, solar panel. And why CDI does not have mass market adoption? Because RO is too powerful. Already Professor Hong mentioned about, so RO is very well established, and already they are trying to optimize the reverse osmosis. That's the reason why RO is a very high maturity index compared to the CDI technology. So this is the still emerging technology, and then just a handful of the technology supplier, such as Siontech from Korea, Ultia from Netherlands, Atlantis Technology from US, EST from China and Italy. So they are the major player of the CDI technology, only 6 in the world, so that we have a limited number of case study for practical application of this one. So we are trying to achieve more case study to expand this technology in the future. And how it works, it's very simple process, absorption and desorption. So you have ion is coming with the water, and then apply for less than 1 voltage, because water splitting is 1.2 voltage. So less than 1.2 voltage you apply, and then your ion will be separate through the cationic exchange membrane and anionic exchange membrane. So you can observe your ions, and you can have a desorption or regeneration. This is the very much social phenomenon, reverse polarity, chemical process, energy recovery can be achieved, and also can be applied to the resource recovery. So you can easily separate observe your ions. So what's the limitation for this technology? So this is the current RO process. The reverse RO is energy intensive, high capital cost. So if you look at the absorption, very slow kinetics and the limited capacity, chemical use, and then electrodialysis, electrochemical process, energy intensive, impractical to scale up. So this is the current limitation, and then we can combine this 3 problem with the very simple solution using the CDI, which will make energy efficient, low cost, and easy to operate using absorption, desorption, and chemical pre-process. So if you look at the research progress, the electrodes are most widely researched area, because still this is emerging technology. People focus on how to develop the better electrodes. So most widely used electrode is activate carbon. Activate carbon has a very high surface area, more than 2,000 square meter per gram, and then this will observe a lot of ion. Also, people can make a much more higher surface area using carbon aerosol and carbon filter, graphene, and then carbon nanotube. However, they are still very costly. That's the reason why we still focus on the activate carbon for the commercial CDI technology. and after that, the application, and 20% how we can apply this technology, and then process development, and then energy recovery. That's the CDI research area at this moment. If you look at the potential application, so brackish groundwater and water softening, heavy metal removal, so nutrient. The MCDI application for selective removal targeted ions are gaining momentum because you don't have to remove sodium chloride and calcium because they are the natural minerals, so we don't have to remove. However, when you have arsenic or some of the heavy metal compounds, so you need to targeted removal can be achieved by this CDI. Also, brackish water, if you have less than 5 grams per liter of the salt, so you can remove that kind of low level with the MCDI. Also, salt water softening, calcium, magnesium, nutrient, phosphorus, phosphate can be removed by this MCDI technology. Also, you can easily attach with the very simple low voltage energy source. The MCDI can be combined with this kind of solar panel. That's the one of the merit because now there's low carbon technology required. If you have a decentralized, also attached with the renewable energy, so this CDI will be one of the very attractive for low carbon technology for water and then desalination. So if you look at the energy consumption, already Professor Hong mentioned about 35 grams per liter of seawater require around 3.5 kilowatt hour per cubic meter. And then when you have a decreased concentration, TDS, 7 grams per liter, 5 grams per liter, so I don't require around 1 kilowatt hour per cubic meter. But when you see the CDI, this green line and then the red line, so you can see that if you apply your CDI for the removal of the 2 grams per liter and almost 3 grams per liter of seawater, brackish water desalination, CDI has better energy consumption compared to the reverse osmosis, so that you can targeting on this 2,000 to 3,000 ppm level of CDI application. Also, we have published several papers in terms of some of the bromide removal and then some of the nutrient removal, lithium recovery, so supported by the Core project. And then I want to focus on some of our result. So this is our seawater desalination in Australia. We have 6 major desalination plants, and we have a 35 gram per liter, and then we are targeting on the bromide. 75 gram per liter in seawater comes to the RO desalination plant after first pass, and salt water concentration is around 150 milligram per liter, and the bromide concentration is around 1 milligram per liter from 75 milligram per liter. And then after this one, second pass, and this will further decrease salt concentration 10 milligram per liter and 0.1 milligram per liter of bromide. In Australia, we don't have much serious boron concentration removal issue because we mix the mostly desalinated water with the fresh water. For example, like Sydney desalinated water around 15%, and then fresh water 85% mixed together. So boron concentration will be very low. That's the reason why we don't really specifically target the boron, but we are targeting on the bromide because bromide is one of the very problematic compound. And this is the natural salt. It's not toxic if you have only bromide, but when you combine with the chlorination, ozonation, and the chloramination, then you create this HO bromide compound, and then this combined with the organic compound, and you produce the bromide organic disinfectant byproduct. And then when you combine with the ozone, and you have bromide, which has very much carcinogenic compound. So in Australia, we have this threshold concentration less than 100 microgram per liter. So we are targeting on this bromide to remove the this ionized form using CDI. This is the experimental condition. We compare with the TDS and then bromide as a background TDS effect. When you have a first pass arrow, 100 to 400 milligram per liter, your bromide, when you increase your TDS concentration, your bromide concentration significantly affected by your background TDS. And we look at the energy consumption. So mostly after first pass, you need the energy consumption around 2.3 kilowatt hour per cubic meter. And then after first pass, your salt concentration is around 200 milligram per liter. And you have a recovery around 85% to 95%. And you need 0.35 kilowatt hour per cubic meter, BWR second pass. So this is the real data from the pulse desalination plant. And then when you compare with your different post-pass TDS concentration, so when you remove with the MCDI, so you consume only 0.1 kilowatt hour per cubic meter with the 200 milligram per liter of your TDS, which is almost 30 times higher, lower energy consumption you can achieve from this bromide. And then we have tested some pilot test of the bromide removal. And then we found out when you have lower desorption flow rate from 1 liter per minute to 4 liter per minute, and then we found out that there is only marginal effect of this bromide removal from 70% to 70.3. So that we didn't see any serious difference of this bromide removal. Also, we compared what's the energy use at the low desorption flow rate from 1 to 4, and then we found out around 0.16 kilowatt hour per cubic meter was consumed by this MCDI for the pilot scale of our MCDI technology. So based on that, to further increase the bromide concentration and removal, and we tried to combine with the bromide resin. So this is anionic change membrane polymer, and then bromide selective resin powder. So we mix together to observe the bromide selectively to increase the overall removal of the bromide, and then it can be observed better with so this is our mixed bromide resin with the anionic change polymer, and then we put onto the carbon electrode, and we tested how much we can improve the overall bromide concentration, and then we look at the first stability with the sodium bromide, sodium chloride, and then we found very much similar conductivity, absorption, desorption within very short period compared to the NaCl. That's the very much similar performance we found out. And then we look at the bromide concentration. So this is the MCDI chloride and then bromide. So this is the bromide MCDI our cell, and then this is the without any bromide membrane cell. So we compare without them with chloride. The chloride doesn't really impact by the bromide MCDI, but when you see the bromide, and then you have a bromide resin and ionic change membrane, you have a better salt absorption capacity. So you have a better absorption of your overall bromide ionic MCDI technology. So we found around 3.4 times higher bromide resin to remove this bromide concentration. Also, we look at the different anionic effect. So we mix together chloride, bromide, sulfate, phosphate, nitrate, iodide, and then we found out the bromide concentration, and then this MCDI and then bromide CDI. You can see how much different from 8% removal till 80%, which means one order of the magnitude we could achieve from this bromide removal using the bromide anion change membrane. So this is our region finding. Also, we look at some of the nitrate and phosphate from wastewater treatment plant. So they discharged a lot of high concentration of nitrate, phosphate. Then how we can recover for this nutrient to make a fertilizer from wastewater, even urine as well as the livestock wastewater. Also, we look at the rhythm recovery. This is hard rock from our rhythm, and they have 40 million ton of the result. And then this is the seawater. We have almost 5 milligram per liter of the lithium concentration, 230 billion tons contained in this ocean. So if we can recover using specific lithium selective ion change membrane together with some nanofiller, can make a better absorption of the lithium compound, as well as we look at not the polymer simping composite. Also, we look at some of the GIF or some of the nanomaterial to have an inorganic simping composite to pass through the only lithium ion through this channel of the GIF. So you have a lithium ion hydrolyzed around 7.16 angstrom, and then this pass through the dehydrated form with the GIF channel, and then you can selectively remove your lithium concentration from your RO brine as well as the seawater. So we try to look at the more high selectivity of the lithium concentration in seawater and then brine. And that's the major conclusion from our study. MCDI could replace second pass BWRO in seawater desalination. MCDI energy efficient for desalination with low TDS, less than 5 gram per liter, and MCDI can be used for selective ion and recovery of the different target with the selective polymer or inorganic simping composite can be developed. So that's our main conclusion. And for the future, we also look at the energy recovery device with activate carbon or some hybrid nanocomposite carbon electrodes, as well as some of the ion change membrane, which will be selectively separate your lithium or some beryllium compound. And as I mentioned, it can be easily coupled with renewable energy. So this is the solar panel can be coupled with the MCDI, so it can be achieved very remote area as a water treatment desalination. Also nowadays we have collaborated with United Nations Development Program to develop off-grid solar powered capacity deionization for Tuvalu. So Tuvalu is located here. The capital is Funafuti. They have 10,000 population. They don't have any fresh water, depending on rainwater or a little bit of groundwater. But problem is that due to the climate change, the seawater level rise, increase the salt concentration of groundwater. So United Nations discussed with us to have solar powered MCDI technology. So last week, you remember we had the COP26 for the climate change conference organized by United Nations, and he is the Minister of the Foreign Affairs in Tuvalu. So he presented this video.
We can't hear the voice actually, Professor.
Dr. Sean? No sound.
No sound, Professor.
So because they now is completely just soaked in the seawater partially, and then we try to make this solar powered desalination. Also, Professor Hong already mentioned about this one. CDI can be replaced with this second pass arrow can be replaced with CDI, and then we can improve the around the 0.2 kilowatt hour per cubic meter of for energy consumption. And this is the decentralized well, the groundwater desalination, because they have some of the nitrate, arsenic, and then some specific contaminant can be removed by this MCDI technology. This is the pretreatment for the microfiltration, and then this MCDI, and then you can easily combine with the groundwater treatment. In the isolated or decentralized small village can be applied the CDI. So just to want to share with the special issue. So we have a COVID-19 impact in desalination. So please submit. This is the one of the hot topic. Also saline water for wastewater desalination, nanofibrous membrane, and osmosis assisted. Professor Hong have this special issue also membrane distillation. So if you have any special issue you want to generate, so please let us know, and then we are happy to keep working together with high quality papers. Thank you for your attention. Also, thank you, Korea, UNDP, and Siontech QNRF for this project support. Thank you.
Thank you, Professor Sean. Thank you so much. So we have a quick, we have a quick question from Joel. What is the capacity of the pilot study in the UAE?
I was told that by Siontech and the Professor Hong, they have a relatively small 300 cubic meter per day. That's the what I was told. Am I right, Professor Hong? 300 or cubic meter per day, or 30 cubic meter per day?
And the one that we installed in UAE pilot plant, CDI.
Yes,
Yes.
CDI. Yeah, CDI.
Less than that. I mean, that one, I remember 50 cubic meter per day.
50 cubic
Okay.
meter per day. Yeah.
It's still
Because
good for the
we are
pilot
testing
study.
this one.
Yes.
Yeah.
Good. Nice to see pilot tested. It looks very nice. Thank you.
Mhm.
Thank you, Joel.
Yeah, Professor Sean, just one final question from myself. Anybody has any question, please? Okay, so you mentioned about the anion exchange membranes, that the bromide ones, they are the best in reducing the best performance. Why is that for the bromide rejection, for the bromide removal?
Okay.
The bromide based.
Yes, this is we incorporated our bromide resin in the anion exchange membrane.
Yeah.
So that this resin is very much specifically, you can observe the bromide compared to the other chloride, nitrate, and the sulfate. So this is the like additional your impact in your anion exchange membrane to have more high selectivity of the bromide concentration. In general, like an anion exchange membrane, you have ammonia-based anion exchange membrane, but for the ammonia-based, we just incorporate bromide selective resin to this anion exchange membrane. That's what is it. We have a more high selectivity. So there are a lot of resin available in the market. So nitrate resin or PFAS, specifically remove the resin. There are specifically you can target on some of the your contaminant, and then we mix together with the anion exchange membrane. with your specific region, and then you will increase the overall your selectivity from the MCDI, from your seawater, even wastewater.
Yeah, I meant like an explanation for the mechanism, like the bromide ones were much more better than other anions, than nitrate or chloride.
Okay, mechanism.
Yeah.
The mechanism is this bromide, specifically we have a design from the, we utilized commercial bromide resin. So we purchased the commercial bromide resin, and then we have an anion change ammonia-based resin, and then we mix together. And then this bromide specifically easily attached on your anion change membrane together with the bromide resin. That's the reason why they have a more easily, specifically you can transport your bromide ion using the anionic change and the bromide resin combined the sympin polymer exchange membrane. That's the reason why we have better selectivity for bromide.
Yeah. Thank you, Professor. Thank you again. And we are really glad to have all of you with us. Our next speaker is, we'll move on. So we have another speaker from the industry. So we have Oscar Rodriguez. Welcome, Oscar, to our symposium, and welcome you to Qatar University and Texas A&M. Oscar is a maintenance director in at Acciona, operation and maintenance desalination, Middle East. He has worked in the water treatment for 14 years, and like in operation and maintenance and commissioning through different water treatment projects, including drinking water, recycled water, wastewater, and desalination infrastructure. He started his career in different projects in Spain, Benidorm, RWTB, Saint Juan d'Espí, DWTB, sorry, or Barcelona seawater reverse osmosis. But also he has experience in international projects such as Altona, RWTB, and Werribee, SRB in Australia, Shangang, WTB in Ireland, RAF A3, and UHB SW seawater reverse osmosis in Qatar. Since 2007, he has developed different roles as a plant process maintenance commissioning manager, depending on the project and the company requirements to contribute with the success of the project. Since 2016, he joined Acciona as Middle East Maintenance Director to participate in the handover and operation and maintenance of different desalination projects. This is, in sum, it's over 100,000 cubic meter per day in Middle East, in the Middle East, including Qatar, RAF A3, Fujairah, and Saudi Arabia, Shuqaiq 3. Oscar, we are really glad to have you with us. And please go ahead. The mic is yours, please.
Hello, Mohamed. Thank you very much. Okay, thank you, everyone. So first of all, I need to thank you for inviting me to this conference. Okay, the explanation that I'm gonna say today is related with the osmosis principles. Okay, so it's not gonna be related as the other ponents regarding the research. Okay, this is more about the basic content, so everyone can understand how the reverse osmosis works. Okay, so let me share my screen. We can start. Okay, all of, can you see my screen? Yes, okay. So this is the second. Okay, this is the summary that we are going to discuss today. First, we are going to talk about why the reverse osmosis desalination in seawater is so important nowadays. We will talk also about the different parts of the process. Then about the principles of the osmosis and reverse osmosis, so we can understand And then we will review just a little bit about the different configuration that we can have in this kind of plants, okay? From the brackish water or the first pass or second pass configuration. So first of all, why this seawater reverse osmosis is so important? Well, there are two main reasons. The first reason is the fresh water availability. As you know, all the water, or most of the water that we have on the planet is seawater, which is around 97%. So this seawater is not drinkable. So only the 3% remain is drinkable, but 2.5 is frozen. So at the end, the only water available for the human consumption, for the energy, for the construction, for all the human activities is a 0.5, which is distributed mainly in aquifers, rainfall, natural lakes. You can see in the graphic the difference between the distribution. So if we develop, this technology, the reverse osmosis for the seawater, if we develop this technology, the main point is that we are able to use this 97% of the water. So in some areas, for example, in the Middle East, where which we have problems with the fresh water, you can process all this water and then you can have fresh water. So the second point is the energy cost, okay? Is the cost in energy terms. And this energy cost is regarding the other desalination technologies that we will see in the next slide. So if you compare the total energy cost from the seawater arrow, facing the other freshwater accessible water, then you can see that the reverse osmosis is around 10 times more expensive than the fresh water. But if you compare the other desalination technologies like the MSF, multi-stage flushing distillation, this technology is very popular here in the Middle East. You can see clearly that the reverse osmosis is a technology that is up to 4 to 5 times cheaper in terms of energy, in terms of electricity, than the MSF. That's why this region, in the last 10 years, there is a kind of a plan to start replacing the MSF technology by the seawater reverse osmosis. Obviously, if you compare the seawater reverse osmosis with the brackish water, obviously there is also a difference, but the brackish water is not seawater, it's just salty water. So the important thing is the comparison between the seawater and the MSF. There is also other technologies, as you can see in this graphic, like the MED regarding the vapor compression or the low temperature, or even the forwarding osmosis that one of my colleagues discussed before. The only problem for these technologies is maybe for the large scale, they are not so popular, or they are not so implemented that the MSF or the reverse osmosis. Just for your information, to have a clear idea about what is the typical cost structure, okay, in the reverse osmosis in the seawater, most of the cost is regarding the electrical power, which can be up to the %. Some of the cost is the capital recovery, is also a big impact. And the rest of the cost is regarding the membrane replacement. In a previous speech, we were talking about the membrane lifetime, okay? By our experience, the normal membrane lifetime in the reverse osmosis will be between 7 to 10 years, okay? Depend of different parameters, depend of the operation, but more or less it's around 7 to 10 years. Then we have the consumption of the chemicals and obviously maintenance and the power. We look in the process itself, we can see that the most energy used is regarding the primary feed pumps, which is the high pressure pumps, because these pumps, the reverse osmosis, we are using high pressure up to 60 to 70 bars. This is not like the previous speech that we were talking about the hyper high pressure processes up to 100 or 200 bars. Still in the normal reverse osmosis for the seawater, we are using between 60 and 70. Okay, so the rest of the consumption is distributed between the water supply, which is the intake pumps, or the product transfer pumps, which is the product water pumps, or any other pretreatment or second stage pumps in case that the second stage is required. So what are the different parts of a seawater RO plant? Well, we have 4 blocks that we are going to comment right now. The first one is the intake. Okay, intake is where we take the water from the sea. So there are 2 main types: the subsurface intakes or the open ocean intakes. So usually the best ones, so the ones that have better quality of water, are the open ocean intakes that also depend of the length and the depth that we take the water. The quality is different. Okay, also the location in the shore, if it is close to a port or an industrial area, this is also different. Just for your information, usually the length of the intake used to be between 1 and 3 meters, and the depth between 5 and 15 meters. But obviously, depending on the project, this changes. Okay, so the next step is the pre-treatment. Pre-treatment is just a matter of different processes that we are trying to do is remove or reduce the quantity of solids and any other contaminant. So these processes can be from a simple coarse screen or traveling band screen up to filtration processes like, for example, this filter, ultrafiltration, nanofiltration, cartridge filters, or also process from the flotation, dissolved air flotation, which is removing the solids. We will see one example later. And all these processes that we are doing is removing these solids and solid waste, that this solid waste will be treated in a wastewater treatment plant. All the RO plants, they have a small wastewater treatment plant as a normal wastewater plant to process these waste. Okay, so the idea of this pre-treatment is to prepare the water, or to increase the quality of the water, or the better quality, to the reverse osmosis rack. Why? Because this technology is very sensitive to the solids. So as much clean in terms of solids or in terms of other contaminants have this water, the better will be the operation. Then we need to do less cleanings for the reverse osmosis, lifetime of them better. So this process that we are doing in the seawater reverse osmosis is we split the water in 2 kinds of water. One, it would be a very less concentrated water, which is that we call the permate, and a high concentration solution, which we call the brine. Brine will be disposed into the ocean, outfall. Meanwhile, the permate will be treated in the post-treatment. Post-treatment is just a matter of 2 main processes. One is the remineralization. So in this process, we add back some salts, especially we are using calcite, to be able that this water will be drinkable for the humans. Okay, and the second point is the disinfection, that we need to ensure the health of the water in the network and up to the tap water for the customers. Okay. So in the chlorination, in the disinfection, that usually we do is, or we can chlorine the sodium hypochlorite, iron dioxide, ozone, or depend of the situation and the parameters. Okay, so here you have some pictures regarding these areas of the desalination plant. This is one picture of the intake. Here we have the pre-treatment. On the right side, you have a UF membrane that is very common in this technology. The left picture is the DAF. This is the dissolved air flotation. So what we are doing is we are creating microbubbles, which is taking the solids up to the surface, and then with the scrubber, we can remove this. So cleaning and remove solids from the. This is a picture of how reverse osmosis racks looks like. You can see there is a metallic structure with a lot of pressure vessels. Okay, in each pressure vessel we have the membrane, the reverse osmosis, where we perform the split of the water, the seawater, in between permate and brine. And also we have, this is, for example, one picture of the remineralization. Okay, these are calcite contactors, so we pass the permate water through these contactors during some time. So this calcite is loaded into the water, so the water get enough salts to be drinkable water. Okay, so this will be the parts of the desalination. This is just a typical PNID, a typical example. So here the water is coming from the intake. We add some chemicals like ferric chloride. This is the DAF that I discussed before. Okay, then we have this filter pretreatment. After this one, ultrafiltration pretreatment, and just after that we have the reverse osmosis first pass. Okay, that we get some permeate and some brine, as we discussed before, and then from this permeate we can process through a second pass. Okay, this second pass also usually we have 2 stages. Can be 1 stage, 2 stage, 3 stage, depend on the quality of the water. Okay. So now, what are the main principles for the osmosis and reverse osmosis? Well, osmosis, as you know, is the natural movement of water across a semi-permeable membrane, okay, between 2 different solutions, okay, with different concentrations. So if you have one solution less concentrate and one solution with more concentration, the osmosis, the natural process, makes that the water will move from the less concentration solution to the high concentration solution in order to equalize the concentration in both solutions. Okay, so at the end of the process, you can have one example, will be this, for example, you have a different water quantity in one of the concentration in the higher, so now it's less concentrate, and the less concentrate stay less concentrate. So this difference, okay, in the height of the water, we call the osmotic pressure. So the osmotic pressure is just the pressure that you apply or to use to make sure that there is no movement between the 2 different solutions. Okay, so based on in the osmosis, we study the reverse osmosis. Okay, so reverse osmosis is just the opposite process. It means if we have 2 solutions with different concentration, we apply pressure in the high concentration side. Okay, we are forcing all the water and a little bit of the quantity of salts to go through the high concentration to the low concentration. So with this one that we have at the end is we have one of the sides which is almost very, very little quantity of solids or salts, okay? And in the other side, we have a high concentration of the solids and the salt. So same as the osmosis, we have the concept of osmotic pressure. Here we have the concept of the NDP, which is net driving pressure. So in this case, the net driving pressure is the pressure that we need to apply in the high concentration side to force the water to go to the low concentration side. Okay, so with these principles, we can use these principles in the industry, in the reverse osmosis industry, to make the seawater, to get permeate water and drinkable water from the seawater. So in this drawing here, you can see this is like a typical pressure vessel. Okay, in this case, this pressure vessel, we have only 3 membranes, 3 are explained now. Okay. So we are feeding the seawater here, the high pressure, around 60 to 70 bars. So the water is going through the membranes themselves, and part of the water, because of the pressure, is collected in a channel, in an internal channel. And this water that is collected is water with a very, very little quantity of salt. Okay, this is that we call the permeate. Meanwhile, the rest of the water is moving through one element to the other. So from the left to the right, the concentration will increase because part of the water is coming to the central tube. Okay, so at the end we have a higher concentration, and this is that we call brine. So this is a typical aeromembrane. Aeromembrane technology started like 60 years ago with different materials, but the latest technology is based in a aeromembrane with 3 layers. Okay, one is polyester layer, which makes the support of the web. Okay, the second one is a microporous polysulfone interlayer, and the third one is the ultra thin polyamide barrier, which is the semi-permeable membrane. So these layers are packed in a spiral gown. Okay, so for example, this membrane, they have usually, it depends of the membrane, of the size, but usually they have around 30 sheets, okay, packaged in a spiral gown. So all these sheets are connected with the central tube. So when the water is coming, they are feeding the water here from the side, and the water is going through the membrane. the water is passing through the membrane itself, so through the polyamide layer, and is collected and go into the inlet channel. Okay, so this will be the permeate. Meanwhile, the rest of the water going through the right side, and it will be more and more concentrated, and it will be the brine. Okay, so now that we know the osmosis and reverse osmosis concept, let's talk about the operational variables that we are using, or we are not using in the reverse osmosis. Here we have the scheme, as I told before. This is the seawater. We have which is the flow, P, which is the pressure, and C, which is the concentration in TDS or conductivity. So this seawater is split between permeate water and the reject. Okay, so first of all, mass balance. We have a relation, okay, by this formula, we have a relation that the flow and concentration of the seawater need to be the summary of the flow and the concentration of the reject plus the permeate, okay? This is a very simple concept. The second one is the recovery. Recovery is the relation, is the percentage between the feed flow and the feed permeate, okay? Which it means, for example, for 100 cubic meter of feed water, seawater, how many cubic meter we can get from permeate, okay? So normally the total value of the recovery in the ADO seawater should be between 40 and 50 for the recovery. Okay, then we have the flux. The flux is the relation between the permeate flow and the area of the membrane. Okay, this is an important value because the designers of the membrane, or the factories, they design the membrane for a specific flux. If we go further for this specific flux, then we can damage the characteristics of the integrity of the membrane. Another one, which is also important, is the concentration factor, which is the inverse relation with the recovery. So the formula is very easy. And the last one is the net driving pressure that we talked before, which is the pressure required to force the water to move high concentration to the loop. Okay, so now let's talk about the different basic configurations in the arrow. You know, the arrow desalination, we can have brackish water or we can have seawater. Okay, in the seawater, we have also first pass and second pass. So this is the basic configuration for the brackish water, but it's also similar to the first pass seawater that we are going to see now. So here you have the high pressure pump, which is controlling the flow. You have a reject control valve, which is controlling the recovery. Okay, so you have the permeate, have the reject, and then you need to take care about that the pressure of the reject, because the reject can be also recirculate to the feed again. Okay, so in the brackish water, because we are using low conductivity, low pressure, this value is not so important, but in the seawater, reverse osmosis is very important. That's why, to avoid this energy waste, the reverse osmosis in the seawater, we're using that we call the pressure exchanger, okay, or energy recovery device, okay? So this is just an example. I'm going to explain how this pressure exchanger works. So in the seawater, in the
Mr.
first
Oscar,
pass,
sorry,
yes.
so we have a limited time, so you may wrap up your talk.
Okay,
Thank you.
yes, I will finish this one and that's it, okay? So to explain the pressure exchanger. So this pressure exchanger, we have the feed pump, okay? That this feed pump feed the high pressure from one side, so we can get the permit. And then we are feeding the pressure exchanger. The pressure exchanger that is doing is the reject, the pressure of the reject. We are transferring this pressure to this feed water. So we are passing through the inlet, we are passing through the inlet again. Okay, so the pressure of the reject gets 1 bar. Meanwhile, this pressure is transferred to the, so we are saving 50% of the energy by using this pressure exchanger. Okay, so this is just another example. And then the second pass configuration is very similar to the brackish water because the inlet, the feed pressure, the feed water, the quality is with low conductivity, so we are using low pressure as well. Okay, so sorry about that. Thank you for your attention.
Yeah, thank you, Oscar. And again, we are glad to have you with us, like another representative from the industry. Thank you so much.
Thank you.
So we'll move. Yeah, thank you. Thanks to all speakers. And now I will move the floor, the mic to my colleague, Dr. Shane, to continue with the rest of the speakers. Thank you all. Dr. Shane, please.
Yes, thank you. Next speaker, Professor Alice Ang. I want to introduce her briefly before her presentation. Actually, Alice Ang is Associate Professor at the School of Energy Environment, City University, Hong Kong, and leading Water and Membrane Technology Laboratory. Dr. Ang received her PhD in Civil and Environmental Engineering at the Hong Kong University of Science and Technology. Before joining the City University, Dr. An was a project assistant professor at the University of Tokyo, Japan. Dr. An has been working in the field of membrane-based water treatment more than 15 years and published over 90 papers on emerging technologies such as membrane distillation, further osmosis, and hybrid RO for removing emerging pollutants and resource recovery. Recently, Dr. An's research has primarily dealt with the fabrication of advanced superhydrophobic and omniphobic polymer membranes, developing a fundamental understanding of and detection method for membrane wearing, scaling, and fouling, and their practical application in MD through industry collaboration. She is currently one of the PIs of the theme-based research scheme in Hong Kong entitled Paradigm Shifting Fully Integrate Compact Waste to Resource Facility, WWRF. Professor Ang, is you are here? Yeah. Okay. So I pass over my mic to you. Your time. Thank you.
Right. So yeah, thank you very much, Shane, for your invitations. And it was very good to hear the previous speaker's talk on the SWRO. Hong Kong is currently constructing the first SWRO, and I think it will be ready in 2023. And so I think we have a lot of opportunity to have a research collaboration. So for the next 20 minutes of talk, I'd like to bring your attention from this pressure-driven SWRO to another type of thermal-based hybrid membrane process, which is the membrane distillations, and with a focus on new emerging material. It's kind of emerging material called the MXene. So we have engineered the MXene material to be used for efficient photothermal membrane distillation. So today my talk will start with a brief introduction of membrane distillation. As I said, this is different from the pressure-driven process, and how we have developed this the MXene material to be used for the solar-driven seawater desalinations. And recently, we have engineered the system to couple with membrane distillations called photothermal membrane distillations. So membrane distillation, well, we discussed the increasing water scarcity and the stringent discharge regulation, which I believe it associated the consideration of unconventional water resources such as seawater, hypersaline water, and wastewater. And these call for emerging technologies to successfully augment the water supply. And the membrane distillation thermally driven membrane process, so which is not affected by the salt concentration of the feed. So there is a reason recently it drew a lot of attention that as a promising technology for treating hypersaline waters that cannot be treated by pressure-driven reverse osmosis and traditional technologies. And since, although the MD is a thermal process, MD can be operated at a relatively low temperature, which gives opportunity to integrate it with waste heat or the solar energy as well. And also it can be operated at a low pressure, and also the produce high quality water. And I just want to show that this is our lab scale of MD process, and generated the permeate from the hypersaline waters. However, thermodynamically, membrane distillation process require large amount of energy to evaporate the water. So the typical enthalpy of vaporization can be 2 to 3 orders of magnitude larger than the Gibbs-free energy for the seawater desalination. So beside the energy consumption required for the vaporization, there are also temperature polarizations due to the convective and the conductive heat loss that need to be minimized to further improve the energy efficiency of the MD-based process, or not to mention the wetting and the scaling and the fouling issues. I'd like to also introduce the another angle that whether its membrane distillation can be coupled with the solar energy to be to reduce the energy consumption. So recently developed in the light to heat converting material have opened up the opportunities for efficient exploitation of the photothermal surface heating, which is kind of self-heating the membrane with low conductivity to maintain higher temperature gradient. So in general, the photothermal, the membrane generate this localized the energy transfer. And then the recent application in the solar steam generation and the photothermal MD has been introduced. So if I give you the simple the diagram to compare the standard membrane distillation process over photothermal MD process. So unlike the standard MD process, where we have to use the extensive amount of thermal energy to heat up the bulk feed water before it enters to the module, the photothermal MD utilize localized heating, as you can see here. So this localized heating induced vaporization of the feed stream directly at the membrane surface. So this significantly improved the energy efficiency of the process by eliminating the need of heating the entire bulk feed water and also reduced temperature polarizations. And also the reduce the temperature polarization. Then the issue is that whether we can develop this ideal photothermal membrane or membrane distillation that essentially possess the highly desired combination of a high photothermal conversion efficiency and as well as strong wetting resistance is the still a challenge. So in our study, we try to looking at some novel material, whether we can functionalize and enhance the membrane performance to be used in the photothermal process to increase the flux as well as prevent wetting. So thanks to the emergence of the various photothermal material, such as a semiconductor and the nanostructured carbon, and also the plasmonic the metal, as you can see here of the literature review, so there are various material has been used in the solar-driven seawater desalination, starting from the gold and the carbon black and many different type of material. And then the recent the paper has also reviewed very significantly the use of different material. So in our study, we have looked into 2D metal carbide and the nitride called MXene. The reason we have we use this the MXene material is because it provides very broad solar spectrum absorption and also the outstanding photothermal conversion, and it has a very hydrophilic nature, so easy to self-stacking, and moreover, especially the unique, the localized surface plasma resonance LSPR effect of the MXene contribute largely to its excellent photothermal effect. So first, in our first study, we synthesize this MXene material and then generated the MXene nanoseed. So typically, this MXene nanosheet was synthesized through the selective etching of an aluminum layer from the raw material, followed by the exfoliations in the deionized water. And as you can see from this figure of different characterization, that after we fabric synthesis the MXene nanosheet, we have characterized to make sure this MXene can give their unique feature of this photothermal effect. And then the first study, we have actually tested this MXene nanosheet, whether it can be used in the solar thermal desalination. And but as I explained, because MXene is hydrophilic material, so the first step we have generated two phase of this hydrophilic layer by decorating this polypropylene layer on top of this the MXene layers. So the benefiting from those functional group and the size effect of MXene and the propylene can be uniformly self-assembled on the surface of the MXene. So we have made these two asymmetric wetting structure of hydrophilic and hydrophobic layer. So when we apply these solar thermal desalinations, so hydrophobic layer, upper layer is beneficial for heat localization and the self-salt resistance. And the hydrophilic bottom layer assure the efficient water pumping and the vapor transport. As you can see, this SMMs, this abundant interlayer channel provide and increase this water vapor the transportations. So when we apply this the MXene nanosheet for the photothermal desalinations, and you can see here that the temperature increase, and also when we compare with, of course, PVDF membrane is not the photothermal, and this evaporation rate is high as 1.4 kilogram per hour per meter square, and the surface hydrophobic layer has a very good salt rejections, and also it provides a very stable water flux. So we have compared our study over the recent publications, and then taking the evaporation rate, efficiency, as well as salt resistance ability into account, they obtained our the MXene membrane always were comparable to most of these membrane-based study which published in recent years. Okay, so after we successfully synthesized the MXene membrane from the raw material, and then the next step is we want to engineer the system with the membrane distillation. So as this is the design concept that from the conventional MD process, we use the novel membrane to use this solar radiance to increase the temperature at the membrane surface. Okay, so that is because of the MXene, the plasmonic effect. And also, when we apply the membrane distillations, so anti-wetting is also one of the issues, and also how to convert this hydrophilic nature of the MXene to hydrophobic was also the question. And so in this work, based on our previous study of converting also the architecture, the membrane surface to be hydrophobic or omniphobic, we have used our previous work, which is using the PDMS and mixed with this MXene powder. So the reason actually we use the commercial PVDF as a substrate is, well, we were able to make this the MXene layer with this inorganic membrane. However, the mechanical strength was not good enough to be used in the membrane distillation process. So we tried to find out the new method we can decorate this mixing layer into PVD membrane to start with. Then, so first we synthesize this mixing powder and then mix with the PDMS to spray coating on the PVDF layer. So you can see here that the on the top of this commercial PVDF layer, we have spray coated this mixing, which is the engineered layer. So it has a dual function like previous solar desalination process, that this mixing layer provide a broad spectrum of the solar absorptions. So when we, during this optimization process, we can see that to maintain the high cross the membrane temperature gradient is due to the membrane with efficient photothermal effect, and which has a very high absorption rate and also the wide wavelengths. And when we utilize this the mixing material into the membrane distillation, one of our concern is if it gives very high thermal conductivity, because it is also it will hinder it will also induce the temperature polarization. Well, because of our coating method, and you can see here, compared to even this PVDF membrane, even though we have used the mixing material into our membrane, the thermal conductivity was even reduced compared to this commercial PVDF membrane. So the thermal conductivity was not of issues after successful optimization. And the temperature, well, this solar absorption was very good, and also within this 3 minutes, you can see the surface temperature was increased up to 85 degrees Celsius. And this is the image from the IR camera on this our PDMS and the mixing base of the membrane over commercial membrane, that how the temperature was increased on the surface. And also because we tried to architecture like a double the re-entrance structures, which will induce the lower the thermal resistance, as well as increase the anti-wetting performance. And also this work is now under revision in the Nature Communications, and still we have to further optimize. And in terms of anti-wetting properties, and maybe many people will ask how this mixing hydrophilic how we can overcome this hydrophilic nature to be hydrophobic. So when we tested this, modified the mixing membrane for this anti-wetting property, actually we were quite surprised that the even this contact angle was increased up to 170, and it has a very super rolling effect. And this is kind of the image of this contact angle over different liquid, the liquid tension, and also it provided this water bouncing effect. So we have also tested our membrane with our homemade anti-wetting monitoring or scaling, and also fouling the monitoring, and it provided very good anti-wetting and also the scaling effect. And here is the flux data through this the impedance study, that it provided very stable wetting and flux. Well, and when we compare this the solar density over the flux, okay, under the different sunlight. Of course, when there is no sun, and the flux between this commercial membrane and our the mixing base membrane has almost no difference. But when under the one sun, you can see that the mixing base membrane, the flux was increased up to 2.8 kilogram RMH. And of course, as a similar pattern, when there is the solar density increase, you can see that the machine can absorb the more solar energy and increase the water flux. And also the flux, well, we have tested certain times, and it provides a very stable flux. And also this is the image that we have used the lab, very small scale of the lab scale photothermal MD process here. And also this is the IR camera image to monitor the temperature increase under the different solar densities. And then finally, we also have compared our study over different literatures. And we found that our study, the membrane outweighs the most of the photothermal membrane distillation membrane and the solar-derived interfacial water evaporators, and especially for hypersaline water treatment. So to conclude, so we have developed this machine engineered membrane that impart efficient localized photothermal effect and the water repellence for sustainable photothermal membrane distillations. And the efficient solar harvesting capability of a machine enable photothermally localized surface self-heating of membrane is due to the to overcome the inherent heat loss at the feed site induced by continuous water to vapor transitions. And this high electrically conductive machines plays structural directing role for the self-assembly of uniform hierarchical polymeric nanospheres on which surface via electrostatic spraying and transforming the intrinsic hydrophilicity into sharp hydrophobicity. So benefiting from this interfacial engineering, the machine-based membrane is endowed with constant high across the membrane temperature gradient, as well as a strong wetting resistance and rendering significant boost in the freshwater production rate. Our data shows up to close to 3 LMH, and the stability when treating hypersaline water, which was 10% of the salinity under one sun irradiations. Well, our work presents a very simple strategy on developing this well-performing machine membrane for potential seawater distillation from the material perspective. However, the emerging machine material membrane are still limited to the lab-scale research, and there is just still a long way before achieving the large-scale application in the futures. And okay, yes. So I think with this, I will conclude my talk. And yeah, so this is the picture of our the group members. And recently, we also developed some new material to participate in industry applications. And with this, thank you very much. And thank you very much for your attention.
Thank you very much. Nice talk, Professor Ang. Since we have a limited time, so we can receive the question. So if the audience have any question, please leave your message in the chat box to directly Professor Ang. Maybe Professor Ang will reply, one by one.
Okay, thank you very much.
Thank you. Next speaker, we want to move to the industry part again. Dr. Saba Solim will present his talk. I want to introduce shortly Dr. Saba. Saba Solim is working at senior technologist at Port GTL in its asset organization for last 4 years, where he is involved in process side of the operation of water and wastewater treatment. Dr. Saba has got a PhD in water resource and has several international publications under his name. In his current role at GTL, he looks after oil water separation systems, effluent treatment and recycling, minimum liquid discharge, thermal desalination, open and closed cooling towers, and boiling feed water system, and so on. One of his recent achievements is to convert the first GLD plant to MLD, which helps bring CO2 reduction and other operational complexities. Before joining Shell, Saba worked in different shell organizations in various parts of the world and has a total experience of more than 20 years in the water and wastewater treatment. Dr. Saba?
Yeah,
you
thanks,
ready?
thanks, Sean, and thanks, Mr. Hassan. Thanks for giving me the opportunity to present the Pearl water treatment management in this forum. Thanks a lot. And through this presentation, basically, I'm going to provide some insights on how we manage water at Pearl GTL. I hope people know that Pearl GTL is the world's largest GTL facility, and water is an integral part of the process. So the molecule of hydrocarbons that we produce in this facility, we produce a molecule of water along with that. So that is the nature of the process. So I'm going to take you through through the water management, how we do it at Pearl, and what facilities are involved and what concepts are involved. Actually, just to give a kind of an insight that this facility is in operation for more than 10 years now, and at the very inception, the whole water management was laid with the concept of circularity. So nowadays we are talking about the circularity, but back then, 10 years back, the whole concept was laid that we would like to basically minimize the water footprint and recycle the water as much as possible. So that is how the whole water treatment facilities have been laid on the site in a very integrated manner. So it's a bit complex as well, but quite fascinating, to be honest. So as all of us know, the water cycle, so that's how we look water at Pearl as well. So we generate water from the process, as I said. Then the water basically moves through the various stages. So from being contaminated with hydrocarbons, then we recycle, then we do the oil water separation, followed by biological treatment, then physical separation of water through gravity sedimentation, followed by membrane applications, which are the ultrafiltration membranes, followed by 3-pass RO systems, and then, as I mentioned, that we follow a kind of full water circularity, and at the back end was the ZLD, where we basically recover the maximum portion of the water, and which we recently have basically converted into make a minimum liquid discharge. I will come to that in the later slides. And then the water is basically put back into the process in the form of steam, in the form of makeup to the cooling tower. So part of water is also lost to atmosphere through evaporation in the cooling towers. So in a greater sense, I would say that it mimics the water cycle. That's how we look at it. And to be honest, water also basically assumes kind of a strategic importance in the state of Qatar, and we are very much tuned and aligned to that strategic concept, and that's why the whole water treatment facilities back then, were designed so that we are basically completely in sync to that concept of fresh water preservation in the state of Qatar, and to add on to that, we, in addition to being a manufacturing site, we also have a research center here in Qatar under the name of Qatar Shell's Science and Technology Center, where a lot of research is being taken at hand to basically minimize the water footprint and to basically innovate the things for the site as we keep on operating, so that we are not left behind. Yeah, so Qatar, so the Pearl GTL, we deliver it in partnership with Qatar Energy now, actually. So I should change this slide. And as I said, it's the largest producer of GTL plants globally. We produce around 140,000 barrels of GTL products per day, and having said that, we also produce an equivalent amount of water, and then we basically reuse the water for a number of applications. So in the background, the facility that you see is the Pearl GTL plant located in Ras Laffan Industrial Estate. So this is the kind of a schematic flow of the process, how the Pearl GTL process looks like. Basically starts from we get offshore gas, which we then basically do the self-cleaning of it. There is some cooling processes happen, and then distillation, and then the methane, and finally the natural gas is basically converted into propane, butane, and ethane. And you can also see on the left-hand side, we also condense some portion of the water in this process. That's a very high-level schematic of the Pearl GTL process. So in this slide, we have a GTL reactors where we basically inject air into the into the gas, and I will not go into that detail. But after we receive the process, the two main processes that take place, which is the biological cleaning, removal of organics in our bioreactors, and then we have the filtration processes, number of them, having said before, which includes gravity filtrations followed by membrane, multiple membrane filtration systems, so that we then clean the water and put it back into the process. These are all preliminary kind of statements that I'm making. I will come to the process in the following slides. Yeah, so the water management involves, as I said, effective reuse, so that we can avoid the discharge of wastewater to the sea. As I mentioned, the water treatment, the water is co-generated with the process. So on a daily basis, we produce new make water on the plant is being produced, which is equivalent to 140,000 barrels of water. So we can't afford to basically put this water into the sea because it's contaminated with hydrocarbons and has many other contaminants in it. So effectively, the design basically entails that we treat this water on site and put it back into the process for a number of applications. So in a sense, we circulate the water through various applications on the site, and minimize the discharge to the sea. And at the same time, if we have to basically procure water from the grid, clean water for a number of applications, that's also minimized in this process, because wherever its applicability is found, that process usage is effectively being basically compensated with this water. So this again gives a bit of a number statistics, how it looks like. I did not to basically give in these guys. So it's all about the scale of the facility. So it all talks about the number of Olympic sized swimming pools. That is the volumes that we are talking about here. But in terms of the total process usage, we are around 2,000 cubic meters of water being processed per hour basis. That is a scale of treatment that you can imagine. So this is how the process is. I will put some time and effort in explaining this process. So on the left-hand side, you see that we have processed water being generated on the plant. That processed water is of two types. One has solids, a lot of solids with it, and the other process is mostly contaminated with organic acids and other organic contaminants. So both these streams go through different types of treatment, like the water which has oily component with it. So goes through oil water separation, through primary oil water separation, essentially the CPIs, which removes the bulk of the oil. This water stream, which has mostly the solids with it, they basically go through the solids thickening, which is nothing but a flotation unit, which is FFU, and also has a dissolved air flotation component associated with it, which actually basically provides microbial treatment, whereby all the solids are floated to the surface, along with the residual oil, which is basically left over from this primary treatment from this second stream, and then then it's come out from the surface, scrubbed out, and goes for the goes for the solids thickening, second stage of treatment. But the water phase basically moves to the second treatment step, which is the biological treatment. And in the biological treatment, we have the DNB, denitrification, and aerobic combination of them, because we also have some ammonia coming into the treatment, coming from the process. So we remove that through the biological treatment. And after the organics are basically broken down to the simpler components, then the second step basically is the membrane filtration. But in the biological treatment, we also consider our clarification, which is the gravity sedimentation part of the biological treatment. Yeah. So essentially, it is a combination of biological treatment and gravity filtration, gravity sedimentation. Once these two-step treatment has happened, water then moves to the next stage of treatment, which is the membrane filtration. So this is purely the solids filtration, whereby we employ ultrafiltration membranes, which are Z-weed membranes, inherently from originally from the GE, then subsequently purchased by different companies, but very versatile membranes basically operate in the in outside in mode of operation, and with a pore size of 0.04 microns. So which means that all the suspended solids are basically removed in this process, leaving behind only the dissolved components, which are then basically treated in the reverse osmosis step. In the reverse osmosis step, actually, in the reverse osmosis step, basically we have the 3-pass RO, which actually the first pass RO operates at an 80% recovery. The second pass also operates at 80%, and the third pass operates at the 50% recovery. Because the third pass, basically the water starts becoming more and more saline, because those are the brine streams from the first 2 passes. And then finally, the third pass RO permeates or is used first pass, second pass at different applications. And finally, the third pass RO brine, which was from the third stage, was basically fed to, which used to be the ZLD portion here. But before I go to the ZLD or MLD concept, the water from the recovered water from the membrane desalination is then basically made as a raw water, and then goes for a number of applications, and portion of this water is disinfected by UV disinfection, goes for irrigation and also exports. And also certain part of the water also, as you can see from this line, is used for making up the cooling tower losses. Because we have evaporative losses, it is a open recirculating cooling towers, so we face some losses there, so we make up this water from this application. And we also receive some blowdowns from the site, which also comes to the cooling tower makeup. But then, as I mentioned, a portion of the water, final brine from all of this process, is eventually basically captured, which used to be 2 years back, or maybe a year and a half back, was a ZLD, full ZLD process, which included a full evaporator and crystallizer system, along with the centrifuge system, whereby we used to produce solid salts. So salts would basically be discharged to the landfill, and the water was basically recycled back into the cooling tower as a makeup from this process, from this side. But we eventually, what we found out in this process is actually the amount of water which we recover is only 5%, because as I said, this process, the membrane filtration, operates cumulatively in the 3 stages, operates at 90%, leaving behind only 10% of the water. And this 10% of water we would basically then put into the ZLD system, and this would recover this balance of the 10% of the water. But this 10% of the water, we, after gaining all of the experience through these years of operation, we found out actually the amount of energy, the reliability issues, and the chemical consumption, and the hassles of operating this ZLD unit is disproportionate to the benefits that we are achieving in terms of recovering this balance of the 10% of the water. So there was a drive in consultation with our with the ministry directives, and also internally the challenges that we are facing, and the amount of salt that needs to be transported off-site to the landfill involved huge amount of road transport, road traffic, road transport around 200 kilometers every day. Around 8 truckloads of salt needs to be transported. So quite an exposure on the road safety as well. No issues faced, but again, the safety exposure was there. And so all in all, there were multiple indicators which were not in favor. So finally, we stopped the ZLD, and we basically started discharging water to the sea. So in that course, we also recognized that we can still recover water through the evaporators, which is less energy intensive. So that is what we did. We finally converted our ZLD process into the MLD, minimum liquid discharge. So in summary, what we are doing now is we are basically recovering maximum portion of the water. So out of the last 10%, we are recovering 7 to 8% from the evaporators only, and the balance of the water, which is a bit more concentrated brine, still meeting the discharge limits as per the MME requirements. Finally, that portion only goes to the sea. So essentially, what we have gained out of this minimum liquid discharge is around 16,000 kgs of CO2 footprint we have reduced. We have reduced our energy consumption from around 8 megawatts to 4 megawatts on this specific unit on itself. And we have also recovered the balance of the water. And then final discharge, which we say is around 3 to 4% goes to the sea. We say that it's in kind of an optimal kind of a thing, because we reduce the bigger chunk of CO2 footprint. We also basically reduce the reliability components of the salt disposal to the landfills, the road transport issues, multiple issues offset with this simple modification that we have done on the site. And then finally, on the other side, the biosludge that we are basically generating, we are basically that is being basically dried now. Of late, we have also included the solar drying of our biosludge. And this biosludge is being basically researched in our technology center. As I said, we have a technology center here, which basically is we have a consultation with number of international universities, along with Qatar University, along with many other institutes here, where we are basically researching how we can utilize this biosludge for non-agricultural crop production, non-food agriculture crop production, and we have some success. We are already seeing some success indicators, especially in the form of cotton production actually. So all in all, this represents a kind of a realistic circular kind of approach that we are following, and we are still researching how we can basically minimize the amount of chemical usage in the various processes, so on and so forth. So that is how the overall Pearl process looks like. I think the next slides will give you a feel of how this whole process is set up on actually on the ground. As I mentioned, I would like to give you a bit of a feel how it looks like on the ground. These are the big tanks where we receive our raw water from these ones, the process water. Then it follows the FFU process, which includes the DAF, which is here. Then this system is the biological treatment bioreactors. Then we have the gravity sedimentation in the big clarifiers. Then this building, which you see actually is the membrane filtration building, where our ultrafiltration membranes are sitting. And these we have two trains, as you can see, laid parallel to each other. And then, but we have a common RO building, which basically then have the 3-pass ROs in it, where we basically treat the water for the removal of the dissolved components. And then on the other side, actually, you can see we have the CPIs for oil removal, which also then eventually feeds back here. We have the cooling towers on the other side. And then we have the final polishing steps in the form of demineralizations or ion exchange processes, where we the finely treated water from the ROs is further fed into the ion exchange systems, where we remove the ions to the level that we make it fit for the boiler applications. That is where the final recycling happens for the water streams. Next slides are again showing how these units look like. So these are the two big clarifiers. For each, we have 4 of them, 2 per train. And this is the DAF unit, where we basically the dissolved air flotation, where all the organics are brought to the surface, along with the thickening actually acts as a kind of a thickener for us for the centrifuges as well. And then once it's scrapped off, and the clean water basically passes to the next stage. These are the pictures of our biotreater. Each biotreater has 2 lanes. This 1 lane. So we have, as I showed you in the previous pictures, we have two trains. So essentially, we have 4 lanes of biotreaters, each one holding around 10,000 cubic meters of water. So 2,000 cubic meters of water being processed through these biotreaters, and with a hold up capacity of around 40,000 cubic meters. So that is a scale of the treatment facility that is that we are having at the site. So these are the pictures of the membrane applications. So on the left-hand side is a cassette of the ultrafiltration membrane cassette, which has modules, 64 modules fit into one cassette. These are the Z-weed membranes, which are then immersed into the tanks. We have 10 such tanks, and we have around 50 of such cassettes in application, which continuously keep on treating these 2,000 cubic meters of water that we process on a daily per hour basis. And then once the water is fine filtered, then we move on to the RO application, 3-pass, and then first pass, second pass, third pass, where in different stages we take out water for different applications. And finally the third pass, or as I mentioned, the treated water is reutilized for number of applications, whereas the brine is basically processed through evaporators. Again, the water recovered from evaporators is basically put as a makeup for the cooling towers, whereas the final brine from evaporators is discharged to the sea, which comprises around 2 to 3% of the overall water being sent out from the site. Yeah, so very close picture of another realistic picture of the facility. And then finally, I think we have the slide that we are currently researching, drying in our solar drying facility, and then currently being researched for application for non-food agricultural crop production, which includes cotton and few more plant varieties. And that's it. I think that gives a end-to-end perspective of the applications that we have at the site, where we were applying different treatment facilities to reclaim the water and put it back for beneficial use applications, and minimizing the discharge to the sea, minimizing import of fresh water from the grid. Yeah, so that's how we manage the water. And I hope this is beneficial to you, because this is the real operation. Yeah, any questions? Happy to answer.
Thank you so much, Dr. Saber. Yeah, it's very interesting. The water treatment in GTL. So since we have also limited time, so we want to move to the next speaker. And if you have any question about Dr. Saba's slide, so you can leave your question in our chat box. He replied one by one.
Thank you very much.
Okay.
Thanks.
Okay. Thank you. So next speaker, Dr. Hyunwoon Ba. Before his presentation, I briefly introduced his career. Dr. Park is a professor of the School of Energy Engineering at Gyeongbuk National University, South Korea. He has over 20 years of experience in environmental energy science and engineering. His research interests include solar hydrogen using photocatalytic and photoelectrochemical technologies, artificial photosynthesis using photocatalytic and photoelectrochemical conversion of carbon dioxide, development of photoelectrochemical cells, photocatalysts, and electrocatalysts for water treatment and energy recovery. He was awarded the Knowledge and Creativity Award in the Ministry of Education, Science and Technology at Korea in 2012, and the Research Excellence Award in 2004 at the Korean Institute of Chemical Engineers, Korea. He has published more than 110 peer-reviewed international papers, and he's the holder of 6 patents. He organized 5 international conferences and meetings related to photochemical and solar energy as co-chairs. He is now supervising 8 PhD dissertations and has supervised 10 MS theses and 2 postdoctoral researchers. Welcome, Dr. Hyunwoon Park. It's time for you.
Hi. Do you hear me?
Yes.
I thank you, Professor Han and the organizing committee for this invitation. Actually, I wait for a long time for my talk. Maybe you also same. And actually, 50 minutes is given to me, but I'm gonna use only 30 or 40 minutes to give you a lunchtime for you, right? Longer lunchtime. So the title is the Solar Water Energy Nexus Technologies status and challenges. Wait a second, I'm gonna use the pointer. Okay, here, yeah. You may be aware of that the importance of the energy and water. Actually, these two resources are really, really important in our human society, and they are strongly, strongly interdependent and interrelated. Just for example, the energy production industry, including the thermoelectric cooling and the hydropower or energy mineral extraction or fuel production, all these industries requires a large amount of water just for cooling or other fine chemical production. At the same time, water production and delivery using the pumping system and treatment system or surface and groundwater treatment system, all these water industry sectors also require a large amount of the energy for these processes. That's why they are strongly interrelated. Just for example, just food production. This is recently this process, this industry, I know that is quite important in Qatar, but the food production need 1,000 to 2,500 cubic ton of water just for a single person in the water. And the reverse osmosis, which is the main topic of this symposium, also need 2.2 kilowatt per ton, the state-of-the-art technologies, while this process still emitting 1.4 to 1.8 kilogram for 1 cubic ton of waters. And wastewater treatment process, particularly in Michigan and other Huron rivers in that watershed, that wastewater treatment also used 30 kilowatt hour per ton while emitting 0.3 kilogram CO2. And the water treatment process and cost is annually increasing by 4% in 2019 in the US, and particularly the thermoelectric power generation, which is around 40% of the existing power plant in the US. Actually, they withdraw the fresh water of around 350 billion gallons per day in 2005 because these thermoelectric power generation systems use through cooling systems. So this amount of water actually accounts for 40%, which is greater than the water required for the agriculture in the US. So this is just an example. So there are many different types of the thermoelectric power generation system. We know that coal-fired power, natural gas-fired power system, and nuclear. But regardless of the type of the thermoelectric power generation systems, these processes usually spend around 50,000 gallons for 1 megawatt hour, which corresponding to that around 50 tons per second for 1 gigawatt hour nuclear power generations. So 1 gigawatt hour nuclear power generation is the global standard. So when you see one dome for nuclear power generation, that power system basically spent 50 tons of water only for a single second. And even the coal-fired power system spend a similar amount of the waters. Okay, so this is an example. So what happened if we suffer from water shortage? In 2003, French country is really popular with the 80% of nuclear power generation in total, and they suffered from heat wave impact in 2003, and in the period they lost 7 to 15% of nuclear power generations just for heat wave impact. The same happens in the Italy as well. And the US, let's see US, this is the southeast areas of US. In these areas, more than 100 nuclear reactors are operating. And in 2008, the drought happens in all these areas, and most of these areas suffered from the electrical shutdown, the blackouts, that system. So these two cases obviously shows that how much water is important in energy industries. Okay, but let's see again our wastewater. This is the German data. So usually one German civilians use, when they spend a large amount of wastewater, their wastewaters is consisting the around 77% of thermal energy. Our wastewater, every water discharged from our household, because we use warm water just for showering. And also this water also has some potential energy around less than 1%, because usually we use stay in the apartments, high top areas. That's why there are some potential energies, also kinetic energies. But these wastewater also contain large quantity of chemical energy, around 22%. So actually the thermal energy is the largest section, but the conversion efficiency of the thermal energy while we are treating the wastewater is very low because the temperature is not that high. But the chemical energy, while we are treating the wastewater, we can actually extract some chemical energy from this wastewater and use this water for our daily living. This is an example, urea. Urea is a main component of human urine. Actually, the urea concentration in human urine is around 0.3 mole. It's large, 22 grams per liter. And this urine and urea are discharged at the rate of 240 megaton per day, every day, 240 megaton worldwide. And this urea, the structure is like that, is 4 hydrogen atoms. That's why one urea has this around hydrogen content is around 6.78%. It's a large amount of the hydrogen carrier. So this urea is the energy density or volumetric and mass energy densities is quite similar to those of ammonia. Recently, ammonia is receiving large high attention because ammonia is considered as hydrogen carrier. So how to store hydrogen? It's a gas. So people are working on the conversion of hydrogen plus nitrogen into ammonia, and later ammonia is converted into the hydrogen. So ammonia is now considered hydrogen carrier. But even urea is the same as ammonia. So that's why recently urea electrolysis has been increasingly studied for hydrogen production or hydrogen carriers. But this urea, there are one primary content in the chemical energy. So that's why we are interested in the solar potential for water energy nexus technologies. So as the previous speaker, who is Alicia An, also mentioned that the standard sunlight is around 1 kilowatt per square meters, can generate on average daily power around 250 watt per square meters per year. And with this power density, if we have devised one solar conversion process or solar conversion systems with 10% energy efficiencies, we can produce hydrogen at around 0.77 grams per second under standard temperature and pressure conditions. Okay, but more importantly, the Middle East countries, including Qatar, have the 5% of the world populations, only 5%, but yet less than 1% of the world's freshwater resources. But your daily average solar irradiation is 2.2 kilowatt hour per square meter. This is twice that the German. Okay, so you have Qatar or these Middle East countries have large population, small population, but they have large solar irradiation. So that means if we combine these water energy nexus technologies, which is driven by the sunlight, these solar water energy nexus technologies can be directly applied to some remote areas suffer from energy supply limits and water shortage, or some coastal areas that receive growing attention as resorts and industries, okay, and require large quantity of water and energy. Okay, so we can just dream that the solar hydrogen plant, this is just a dream. One scientist proposed this idea, renowned scientist proposed this idea, but it's just an idea. If we have one solar hydrogen plant, the area is around 25 square kilometer, like that, 5 kilometer and 5 kilometer solar hydrogen plant. We don't care the type of the solar conversion process. We don't care. Just let's assume that this process can produce hydrogen from water with the solar conversion efficiency of 10%. This is a minimum limit for practical application of solar hydrogen plant. And through this process, we can use sunlight around 7 to 8 hours for a single day. We can produce 570 tons hydrogen per day. Okay, so if we make this solar hydrogen plant 10,000, that means we need 250,000 square kilometer area. But this is only 1% of the Earth desert land. So with this 10,000 solar hydrogen plant, we can produce 5.7 million tons hydrogen, which is 1/3 of the energy needed in 2050. So potential is really, really huge. As long as we have 10% conversion efficiency systems, okay? This shows that how much these solar conversion systems has the potential. So there are many, many different types of solar conversion systems. So I'm not going to specifically explain the dismerit about these systems, but they can simply classified into the photocatalytic, conventional, photoelectrochemical, and PV electrochemical system. There are many, many different types of these systems, but this is still early stage and not commercialized, not practical yet. And the most practical one is PV electrochemical systems, because the efficiency of PV is now arriving around more than 20 or 30%, and electrochemical conversion systems now, the efficiency and durability is still growing up. Okay, so we can just simply design this kind of simple electrochemical system driven with the photovoltaics or direct sunlight, whatever. The sunlight is not important in this factor. Anyway, we can design, and through this electrochemical system, we can treat the wastewater or saline water while we are producing some hydrogen from water, or producing CO2 conversion, or we can drive any kind of the value-added chemical production processes in a single devices. So there are many, many different types of. So I'm not going to specify details about this system. So very simply, the electrochemical system has an anodic system and cathodic system. In water, in aqueous system, in anode, we can split water into hydroxyl radicals with 1 electron oxidations, or you can split water into hydrogen peroxide as chemicals with 2 electron process. You can produce oxygen with 4 electrons. You can produce ozone with 6 electrons. So only with water, you can produce hydroxyl radicals, hydrogen peroxide, oxygen, and ozone. But in the presence of some chloride, like seawater or brine or brackish water, we can produce some chlorines, reactive chlorine species. At the same time, on the cathode, we can reverse all this process into oxygen reduction reaction, or you can produce hydrogen peroxide, or we can produce peroxide radical anion, also hydrogen production. Also, you can, when you produce CO2, we can produce formic acid and CO or ethylene. When you waste the nitrogen, we can produce ammonia. There are many, many different types of the chemical production systems are available. Okay, so all these oxidation reactions and reduction reactions need a different number of electrons and operating in different potentials. So we can design, we can couple one oxidation reaction with the other reduction reaction in a single devices. Okay, so hydroxyl radical, I'm gonna first mention the hydroxyl radical. This hydroxyl radical is the second most reactive species in the world. The fluorine is the most reactive, and the hydroxyl radical follow the fluorine. And with some electrochemical or photoelectrochemical system, whatever, the hydroxyl radicals are produced through the one electron oxidation of water, and these hydroxy radicals are absorbed and later they used for organic compound oxidation. And also these, we can produce ozone. In this case, ozone or hydroxy radicals, they are interrelated. They are transformed into some hydroperoxide radical or peroxide radical or hydrogen peroxide. So all these reactive oxygen species are circulated among themselves, changing each other's, transforming each other's. Okay, and these hydroxy radicals, this table shows the reactivity of hydroxy radicals. Here, these hydroxy radicals react with the methanol at around 10 to 9 mole per liter per second. These most of organic compounds, the rate constants are 10 to 9. This is diffusion limited reaction rate constant, indicating that the reaction rate is super fast. And also other organic, inorganic reactants are rapidly transformed into the other species with hydroxy radicals. Okay, so when we look into the wastewater treated through the biological systems, we are surprised that there are more than 30 some compounds are discharged without treatment, although this is secondary biological treatment systems. So because of their levels are quite low, and this is not treated with the biologically. But when we use the hydroxy radical, all these substrates, the pharmaceuticals like benzyl fibrates or diazepam or ibuprofen, all these pharmaceuticals, untreated chemicals from the biological treatment systems are rapidly, quickly decomposed by the hydroxy radicals. That means still hydroxy radicals are really reactive for most organic compounds. Also, we can produce the ozone through our electrode like that. This is this typical conventional electrode which are generating hydroxy radicals, but these electrodes do not produce ozone at all. But when our electrode modified from the conventional electrode, they are starting to produce the ozone quite efficiently, around 30% energy efficiency. And this ozone, we are successful in decomposing some the algae like the obliquus and rain hardity, and our electrode is quite efficient in decomposing the algae because these ozones are selectively and efficiently produced. Also, we can treat the urea, as I mentioned, the urea at the same time we can produce hydrogen in a single devices. So this is our electrochemical system, and this electrochemical system treats the urea or urine into the nitrate, ammonia, and at the same time you can produce hydrogen through the photovoltaic systems. So as the urea concentration increases, more nitrate and ammonia produced. At the same time, hydrogen is produced more in the case of without urea. So actually that means urea is hydrogen carrier, and we can produce hydrogen while treating urea. So this is a little bit large scale, the reactors, we can use photovoltaics and make many arrays of electrode, and through this electrode we can treat the urea or any types of the wastewater while producing hydrogen, and the collected hydrogens is flowed to the fuel cell for the nighttime applications. Okay, so at the same time, we can just devise other system. In this case, we can oxidize arsenic-3, which is toxic for human. We can oxidize this arsenic into the arsenic-5, which is less toxic than the arsenic-3, while we are making the hydrogen peroxide through the cathode reduction. In the case arsenic-3, while arsenic-3 is oxidized into the arsenic-5, 2 protons are released, and these 2 protons are moved to the cathode through the proton exchange membranes, and this oxygen reduction occurs with these protons, and the hydrogen peroxide is produced. This is a quite valuable, high expensive the chemicals, and you see that the hydrogen hydrogen peroxide is continuously produced with the energy Faraday efficiency around 100%. At the same time, we can still produce arsenic 5 through arsenic 3, so we can drive both systems in a single devices, hydrogen peroxide production with the 100% Faraday efficiency and the arsenic oxidation at the 80–90% energy Faraday efficiencies with the sunlight. Okay, but the problem happens that the sodium chloride is everywhere. All the previous system shows that the wastewater without chloride. But as shown here, the sodium chloride is everywhere, and there is a fuss to still find the sodium-free salt or sodium-free waters. So in chloride level in unpolluted water around 0.3 millimole, and the rivers in UK, I don't know why, their rivers are quite high concentration of chloride, 1 millimole, and the agricultural water also 7 millimole. Industrial water, yeah, larger, 14 millimole, and the aquifers, the aquifers near to the seawater is a larger concentration, 30 millimole, and still I don't know why. This is quite curious for me. Contaminated water in Philippines, 4 millimole, and the produced water, large and brine seawater, most of types of the water has chloride. So what happened in chloride? If in the water with the chloride, without chloride, most of the water oxidations, oxygen evaluation or hydroxy radical generation process. But in the presence of chloride, water oxidation stops. Instead, chlorine evaluation reaction proceed more efficiently than the water oxidations. So in the presence of chloride, hydroxy radicals react with chloride, and this intermediate produced, and there are many chlorine species produced in electrochemical systems. So let's compare the hydroxy radicals, which are primary oxidant without chloride, and also other chlorine species. These chlorine species are less reactive than the hydroxy radical for some specific organic compounds, but for the other chemicals, they are quite comparable. So chlorines, recently chlorine oxidation is receiving more and more interesting because this reactive chlorine species are used for partial oxidation. For example, ethylene into ethylene oxide, propylene into propylene oxide. So in the presence of the chloride, like the saline water treatment, this chlorine is now oxidized into the reactive chlorine species like hypochloric acid or hypochlorous at some neutral pH. And this continual production, when you put some kind of organic compounds, these organic compounds are rapidly decomposed. And when you put the spiking again, the organic compounds, they decompose and decompose again and again. And at the same time, CO2 is produced. But then also hydrogen is continuously produced over time, and more hydrogen is produced when you put the organic compounds. So that means all these systems, this saline water treatment system also work very efficiently with the photovoltaics while producing hydrogen. Also, arsenic oxidation also proceed with the chloride. In this case, these free chlorines or reactive chlorine species are produced. These arsenic 3s are oxidized with arsenic 5. At the same time, we can drive CO2 reduction into formic acid in a single devices. So this single devices shows that we can drive in the saline water system, we can drive arsenic oxidation. At the same time, the formic acid production from seawater with the Faraday efficiency nearly 100% efficiency. So this means that our design system still working in the saline water. Okay. Also, we can use this saline water in desalination system. So this is a simple system. We can put the saline water like the seawater or brine water, and this anion exchanging membrane, this is a cation exchanging membrane, and when you apply some potential with the sunlight, this chloride is selectively moved to the anolyte, and sodium selectively moved to the catholyte, and this chloride is converted oxide into the reactive chlorine species, and this species actually oxidizes wastewater into clean water while we are producing hydrogen, and the clean water desalinated salted waters in a single devices. Okay, so for that, we devised some semiconductor or photovoltaic materials, and as shown here, this saline water is rapidly desalted. At the same time, the anion and sodium and chlorides move to the anolyte and catholyte. At the same time, urea as a primary organic compounds are decomposed with the chloride desalted from the saline water. And also we produce some hydrogen with the sodium ions, concentrated sodium ions in the catholyte. So through this system, we can produce desalted water and hydrogen, at the same time treat the organic compounds in a single devices. So we can make some stacks through these many anion and exchange membrane stacks. We can drive a faster and more efficient desalination system while treating water and produce hydrogen in a single devices. So as shown here, as we stack more desalination water systems, urea concentration is rapidly decomposed. At the same time, the conductivity of saline water rapidly decreased because of desalination, and the hydrogen is produced at the same time. All these three independent processes happens at the same time, and the specific energy consumption for desalination of this brackish water is around 1 kilowatt per cubic ton. So it's quite low because this energy is partial of this energy is provided by the sunlight. Okay, also we can devise some electrochemical desalination system while producing the converting CO, capture the CO2 emitted from the fossil fuel coal-fired power plants. So this the same scheme, but when we use the electrode, not the semiconductor electrode, just electrode, we can produce chlorine, reactive chlorine, which is responsible for the urine decomposition. And at the same time, we can purge the emitted CO2 from the coal-fired power plant, and this captured CO2 is converted to the formic acid in a single devices while desalinating the saline water in a single device. These are the stack systems. So all this also data shows the same result, that the urea is rapidly decomposed and the conductivity of the saline water decreased as well, regardless if this is brackish water and seawater, and also formic acid produced with the 100% ferrous efficiencies. And overall, so when you couple the photovoltaic system to drive overall system without any the electrical power generation from the plug, and the overall system operating as standalone, and the efficiency overall solar to desalination efficiency is around 18% is we achieved. Okay, finally, recently also we are working on this field. Also, we use the anion exchange membranes and cation exchange membranes, and also we inserted bipolar membranes in these two areas. And while we are desalinating the seawater, actually we are making hydrochloric acid and sodium hydroxide at the same time. And in this area, we are producing oxygen and producing hydrogen in a single devices. So through these stack arrays, I'm not going to show the full data because still work manuscript now in preparation. So we are now making acid, base, hydrogen, and clean water together from the seawater in a single devices. So this means that still there are many large room for further modification and produce more valuable chemicals through these systems. Okay, so the summary is like that. So I'm going to show this one. For decentralized in-situ production of solar fuels, water must be supplied continually and inexpensively and readily acquired. So that means we need use the seawater in the remote area, and the sunlight is primary energy source. And at the same time, if we use the clean water or desalted water through this system, the cost effectiveness of the system should be much, much bigger than the conventional water treatment or desalination systems. Okay, so this is my group members, and particularly I'm gonna appreciate my long friends, collaborators, the Professor Han, now shown here, and the Sunhee Yoon, also Texas University Qatar, A&M Qatar, and my advisor Won-Young Choi, and my collaborator in Japan, Tokyo Institute of Technology, Kazuhiko Maeda, also one of my postdocs working with him in Tokyo, and Csaba Janaki, University of Szeged in Hungary, also one of my postdocs working with him in Hungary, and Michael, my postdoc advisor, Karte. Also, all these collaborators I'm working with for the solar conversion systems. Okay, this is what I prepared. Thank you for all the audiences. I think that you still you feel starving and maybe bored because of long. This is really long. I mean, morning session. So I don't know why you are making this long session. Okay, so this is what I prepared. Thank you.
Thank you, Professor Park. So because I expect you deliver, very, specific, the good technology of to all audiences. That's why I put your, keynote speaker at last section.
Okay,
so,
thank you,
yeah.
thank you.
Audience, do you have any question for Dr. Professor Park, the presentation?
So I really encourage you to have a meal. Okay, so I know, but I've been Colorado so many times. So how do you feel right now? I fully understand. Okay.
Is there any questions?
Okay.
Okay.
So still here, this is also meal time. So now it's 7 o'clock. So okay.
You're hungry, yeah?
Yeah,
You're
right.
You're dinner time and our lunch time.
Yeah, right now. Yeah, right. Yeah, you're right.
Yeah, if there is no questions, so somebody ask, let's see, one question, interest work, any primarily techno-economics analysis of cost of desalinate through seawater electrolysis with the BPM, AEM, and PEM, while it's producing hydrogen. So as compared to direct desalinating, followed by hydrogen production through conventional electrolysis.
Oh, yeah. Actually, we didn't have the TEA, techno economic analysis. Actually, we don't have such skills. So, Ahmed, if you have some kind of skill that is techno economic analysis, I really welcome to collaborate with you. Actually, I don't have that knowledge, so I'm searching, but these guys are really, really busy because many scientists contact them just for techno-economic analysis. So I'm going to really welcome for collaboration for the analysis. But I'm sorry, I don't know. But actually, membrane price is quite high, so I'm a little bit skeptical in a small scale. But if we make the large scale, it can be a more cost-effective and economy. I hope.
One people ask you, can we characterize the hydrogen source?
What do you mean? Hydrogen source is water. I mean, although there's wastewater, saline water, regardless of type of water, hydrogen is always come from the water. That is confirmed by the isotope experiment. Is well on. Is quite well on. Okay. Yeah, isotope. Oh, yeah.
Yeah,
Okay,
last
right.
question.
Right,
Yeah,
same. So yeah. So yeah, regardless of the wastewater, for example, when you put when urea, for example, urea is also hydrogen, but the primary hydrogen, because the hydrogen actually come from the water reduction. Urea, while urea is decomposed into the water or nitrogen, that urea does not directly contribute to the hydrogen gas. But we use urea as a chemical energy because the Gibbs energy of urea is negative, okay? Takenabe group in Tokyo. Oh yeah, I'm gonna check, but that can be controversial, but we can simply calculate the number of organic molecules or number of hydrogen linked to the molecules and the number of hydrogen we produce. When you compare both number of moles, number of hydrogens, or amount of hydrogens, you can find that the hydrogen, produced hydrogen is much more or larger than the organic compounds we used. Okay, so that some fraction or tiny amount of hydrogen can come from the oxidation reaction, but that is tiny, I believe. Yeah, but quite interesting. So Takenabe group in Japan show hydrogen coming from photolysis of the buffer, hydrogen buffer. Well, okay, Ahmed, yeah. Ozone, hydrogens can be simply quantified using the gas chromatography. You can visit many chemical engineering labs in your school campus. It's quite simple, quite straightforward. And ozone, quantifying ozone is also quite well known. There are some UVB spec or some calorimetric, UV spec with the calorimetric. So it's quite well known. It's simple. So we do not analyze the dissolved ozone. We just measure dissolved ozone. Yeah, quite simple. I'm gonna give you some papers if you want.
So here is a last question. I don't know, you already covered this one. So anyway, how do we differentiate from hydrogen coming from biogenic bacteria and from corrosion reaction?
Oh, some question. Hydrogen coming from biogenic bacteria from corrosion reaction.
You didn't cover any bacteria and corrosion reaction, but based on your knowledge, so can you?
I'm sorry, I can't catch the primary point you are asking. Corrosion reaction in biogenic bacteria. How do we differentiate? Oh well, I think this is out of scope of my talk, so we can discuss in this one through email or the other one. Okay, maybe the out of scope.
Yes. Okay. So we covered all questions. Thank you very much.
Ask a very simple question?
Okay.
Yeah.
Sure.
So yeah, Professor Bach, very interesting talk. I have a very naive question. So it's very interesting.
Hi, Alicia. Yeah, this is my first time to see you. Your talk is really interesting and impressive. So Maxine is quite interesting materials, and your publication history is really impressive. So actually, I thought that later I'm gonna contact you regarding the solar desalination, also including Kara. Yeah. Okay.
So I have a very naive question. So yeah, I know the water splitting generate hydrogen, and then now so your study from urea to hydrogen. So what will be the energy balance? How much energy is needed to break down and per hydrogen generations?
While treating the urea?
Yes.
Actually, you know that urea oxidation plus hydrogen production, that is, let me see, overall Gibbs energy is exergonic, but because urea oxidation is nearly minus 0.0 some voltage NHE, hydrogen electrode. So the overall Gibbs energy is negative, but the urea oxidation is 6 electron transfer reactions, and the hydrogen is 2 electron reaction. Also, urea station, while oxidizing urea station actually produce many intermediates like the nitrate, nitrite, or ammonia, and those kind of molecules are much more difficult to be oxidized. So recently, urea electrolysis is quite popular, particularly in Chinese peoples. I don't know why, and also we are working on that. But still, urea oxidation, according to our research, require large amount of the overpotential. Okay, really large. It's working maybe 0.76 volt versus RHE, really large. Although that means the overpotential may be nearly 1 volt. Yeah, so that is really disappointing. So we are trying to, so some people increase some temperature, because at room temperature, there are large overpotentials, so reduce the overpotentials. Some people are working on the solid oxide fuel cell system at high temperature, even the ammonia oxidation, same story. So we can devise urine fuel cell like ORR and UOR, but does not work at room temperature. That is critical issue recently. Yeah.
Right. Thank you very much. Yeah. So look forward to have some collaboration in the future.
Yeah, I love Hong Kong as well.
Thank you. Yeah, it's great platform to have opportunity for collaboration, potential collaboration. Since we don't have further questions, I wanna pass my mic to Dr. Mohammed Hassan to wrap up our section.
Yeah, thank you, Dr. Shane, and many thanks for all presenter. Very nice work actually, and if you don't mind, be ready. We'll take a final group picture together. So please be prepared. So Ms. Noor, please go ahead.
Yes, I just would like to ask all the speakers to open their camera.
Yeah, please focus on the camera. So Ms. Noor, ready? Go ahead. Are you done, Noor?
I'm already taking photos, but just bear with me. I would like to take as much as I can.
Okay.
Okay. Just to smile and okay, one last one. Great. Thank you so much.
Yeah. Thank you. Thanks again for all the speakers. We were really honored, myself and my colleague, Dr. Shane, to have you with us, as well as our colleagues from Texas A&M. And we look forward to see you all next year in Qatar, hopefully in person and in the World Cup as well. Thank you. Thank you so much.
Thank you, everybody. Thank you.
Bye-bye.
I hope to see you all the next year in Doha.
Sure. You are all welcome to join us. Yeah. Thank you.
Bye-bye.
Thank you to all speakers. Thank you. Bye-bye.
For all the attendees, please note that we will have a poster session right now.